Good afternoon, everyone, and thank you for joining us for today's workshop. We're going to get started here. We're a little bit behind schedule, and I do apologize for that. But before we do, I'd like to go over a few housekeeping items with you. The first thing I'd like to draw your attention to is our chat pod, which is located on the left-hand side of the screen marked chat. This chat pod will be the best way to communicate with us if you have any questions regarding today's material. All questions pertaining to the material will be retained until the panel discussion that will be held at the end of today's presentations. We have 4 presentations today, so please feel free at any time during the presentations to type in a question, and we'll hold it and get it answered during the discussion. This chat pod is also the best way to let us know if you experience any technical issues. If you do experience any technical issues, please feel free to type them into the chat pod, and either myself or one of our customer service representatives will make sure to get you taken care of. That up? There we go. Boy, that's a little better. So, all of today's audio is going to be streaming through your computer speakers. So remember, if you have any technical issues with your audio or your live feed, please let us know in the chat pod. We'll be sure to assist you. With our new platform, we would like to point out that using the web browsers Google Chrome or Mozilla Firefox will provide you with the best user experience. You will also see the closed captions below the live feed of the event, should you need to refer to them. Please remember to hit the play button on the live feed screen to make sure you're able to see the slides that are being presented. If for some reason your audio or live feed freezes, first thing you should do to troubleshoot will be to refresh your browser and then hit the play button again on your live feed to try and reestablish your connection. So because we are a little bit behind, we're going to just dive right in. So thank you for joining us today. All right, everyone. We're going to go ahead and get started with today's presentations for Module 7 of the Probabilistic Genotyping Workshop Series. My name is Tyler Rabel, and I'm with the Forensic Technology Center of Excellence, and I'll be your technical host for today's module. Today's module will be on the topic of uncertainty and limitations of probabilistic genotyping systems. Moderating today's workshop will be Dr. Tamara Moretti with the FBI Laboratory. Dr. Moretti is a research biologist for the DNA Support Unit of the Federal Bureau of Investigation Laboratory. She earned her PhD in genetics from the George Washington University for her research at the National Institute of Health. 23 years ago, Dr. Moretti joined the FBI Forensic Science Research Unit, where she performed research, development, and validation of PCR-based methods for the analysis of nuclear and mitochondrial DNA. She's lectured extensively and trained forensic scientists and attorneys throughout the U.S. and internationally. At the FBI, Dr. Moretti has also held positions as an examiner in casework and convicted offender databasing operations, and she has managed the FBI's DNA training and validation programs. As a disclaimer, the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenters and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. Dr. Moretti has developed this series as a forum for experts in the field of statistical genetics and probabilistic genotyping to share their knowledge and experience as the forensic DNA testing community transitions to probabilistic genotyping. She will be moderating today's module. I'd now like to hand the microphone and the platform over to Dr. Tamara Moretti.
Thank you so much, Tyler. Welcome, everyone, to our session today. Today, we are going to be speaking, continuing in our series on probabilistic genotyping of evidentiary DNA typing results. And for those of you who have been with us for the past several weeks, we have begun with our introductory material and moved into discussing statistics associated with probabilistic genotyping, looked at software and validation, communicating likelihood ratios. And then last week, we heard from those who have experience in presenting this type of evidence in court. So today we have a very important, I think, session today because we're focusing on uncertainty and limitations in probabilistic genotyping systems. And our speakers today are very well known and very well published researchers and practitioners in our field who have done validations and studies and developmental work to be able to contribute to the discussion today on profile complexity, uncertainty in number of contributors to a mixture, decision-making, error rates, transfer and persistence, hierarchy of propositions, and activity level propositions. Those are just some of the topics that we're going to be touching on today. Before I move into the introductions of the speakers, I wanted to update you about our next and final session that's going to be moved from July 10th to July 17th. Joe Bright and Ted Hunt are going to be joining us to lecture on some of the topics that we've had questions about or of particular interest as we've moved through the series. And then we're going to have some other speakers that have joined us in the past weeks to take questions and answers and focus on specific topics. So I hope that you all can join us in 2 weeks, and we will shortly be updating the website to reflect that change and allow you to register for that upcoming session. So today, again, we're here to share our knowledge and experience in probabilistic genotyping and have great speakers that have graciously offered their time to join us today. One of our speakers is Dr. Amki Khalib. She studied mathematics and physics at the universities Oldenburg and Kiel in Germany from 1990 to 1996 with diplomas in the area of biostatistical biophysics. From 96 to 2003, she worked at the mathematics seminar in Kiel University in the group of Professor Hugh Losler. Her PhD in mathematics in 1999 was about statistics of hidden Markov models. Since 2002, her research in this area of statistical analysis and stochastic modeling on genetic data, with her current research interests in statistics for forensic genetics, stochastic modeling, and statistical procedures in population genetics, genetic epidemiology, and statistics for ancient DNA data. Currently, she's employed at the Institute of Medical Informatics and Statistics at Kiel University and as a senior lecturer and researcher since 2003. In 2018, she submitted her habilitation thesis in statistical methods in forensic genetics. Her work in forensic genetics focuses on the temporal behavior and mutation models of STR loci, Y chromosomal haplotype frequency estimation, and match probabilities, and advanced statistical issues in mixture analysis, such as uncertainty and the number of contributors. Another speaker today is Zane Kerr. He is a senior scientist currently with the Institute of Environmental Science and Research Limited, ESR, in Auckland, New Zealand. He completed his Bachelor's of Science in Biomedical Science and Forensic Biology at the University of Technology in Sydney in 2007, graduating with honors. Shortly after graduating, Zane commenced his professional career as a forensic biologist at the New South Wales Forensic and Analytical Science Service in Sydney, Australia. During this employment, he developed a strong interest in the statistical evaluation of forensic DNA profiles and completed advanced training courses in star mix and true allele. He completed a certificate of advanced studies in statistics and the evaluation of forensic evidence at the University of Lausanne in Switzerland. And he was the FASS representative within the Australasian Statistics Scientific Working Group, a group that's comprised of forensic scientists from each of the Australasian forensic laboratories tasked with providing guidance on statistical issues pertaining to forensic interpretation. And we are also pleased today to be joined by Dr. Klaas Vluten. He's currently working at the Netherlands Forensic Institute, where he has held the position as a statistician and as reporting officer in kinship cases. In addition, he's an endowed professor at the VU University of Amsterdam for forensic genetics and at the Department of Mathematics. His interests lie in giving mathematical description to problems in forensic genetics, usually in kinship analysis as well as mixture analysis. but also more generally. One of his current activities is the statistical modeling of DNA mixture profiles. Amongst other things, he's devised and programmed a semi-continuous model for the evaluation of likelihood ratios for DNA mixtures that is detailed in the references that he has provided for our webinar today. Dr. Sloeten studied mathematics in Leiden, the Netherlands, and obtained his PhD from the University of Amsterdam in 2003. Since 2008, he's worked at the NFI. His research and publications are concerned with DNA databases, familial searching, the effect of uncertainty on the weight of evidence, DNA mixtures, and the theory and philosophy of statistical evidence and forensics in general. He's currently writing a book on forensic statistics that is due to appear next year. He teaches as well regularly at the university and has a course on forensic probability and statistics for mathematics students, another one on statistics in general, and also teaches DNA statistics at NFI. And our final speaker today is Dr. Bianca Scuda. She's a postdoctoral fellow at Deakin University and the Victoria Police Forensic Services Department. In November of 2017, she completed her PhD at Deakin University in collaboration with the police service, investigating the variables affecting the transfer, persistence, prevalence, and recovery of DNA in various forensically relevant scenarios. She holds a Bachelor of Forensic Science with honors with a major in forensic biology as well. She is a long-term member of various forensic societies, including the Australian and New Zealand Forensic Science Society, for which she is also a committee member of the Victorian branch. She's attended and presented at multiple national and international conferences and published papers in key forensic journals. Her current postdoctoral work expands on her previously published research on DNA transfer and persistence, prevalence and recovery, with an end goal of increasing our knowledge on DNA-related activity level issues and providing much needed data for those requested to provide expert opinion. So you can see why we have invited these speakers to join us today to talk about these very important topics. So I'm grateful to you all for joining us as presenters. And with that, I would like to invite Dr. Sloeten to unmute his mic and begin sharing his screen for our first presentation. Thank you all so much for joining us today.
So, hello. I hope you can see my screen now with my presentation on it. So let me see how to do that. I did see it, but yes. So I'm just going to assume you can see it. So my talk is about some considerations on uncertainty that come into play when you're doing statistical modeling of DNA mixtures. And basically, I'm going to recap a little bit what the original problem is that we have, and then try to make some analysis with kinship evaluation, where exactly the same or analogous and similar problems come up that do in mixture analysis. And I think it's insightful to compare them with each other, and so as to be able to see which ones are, say, important and which ones are maybe less important. So I'm going to identify several sources of uncertainty that we're going to discuss. But let me first get back to the original question. Did a person of interest, which I will call S, contribute DNA to a trace P? So what do we have to make a statement about that? Well, we have a profile from a trace. I'm calling that M. So the profile is a collection of alleles and their peak heights. And then we also have the DNA profile of that person that we're interested in. Let's call that G. And maybe we know some more. Maybe we have some DNA profiles of known contributors that I'm going to summarize into the symbol I. So the question is, did this person of interest contribute? And of course, people would like it if we would say yes or no, but we can't answer a question like that, except perhaps when there is a clear no. So what can we do instead? We can say whether or not there is evidence in favor of the possibility that S contributed. So what do? Well, we need to explain how that profile came about. So we have seen that we cannot deny it's there. We don't need to predict it anymore in a way. We need to explain it. So if we focus on this suspect, say S, then either S contributed or S did not. But if S didn't contribute, we're going to need another explanation for the profile because it came about some way or another. So who was it then? And also, who else is in there apart from S? Who are they? So typically, we will assume that all of the unknown contributors are unrelated to S and to each other. In other words, we're going to suppose that we know nothing about them other than that they belong to a certain population that we are working in. We could extend that to relatedness, but then there could be very many possibilities. For example, if we would consider that a mixture has 3 brothers and 2 cousins as contributors, for example, we could go very far into setting up possible explanations for that profile. But usually there's the single one of them that stands out as being a very logical one to consider, unless, of course, it's being advocated in the course of a trial or something. But without any reason to think otherwise, we're going to always assume that all of the persons that we know nothing about, that we really know nothing about, and we only know that they belong to a certain population. And then that amounts to saying that all of them are unrelated to each other, to S, or to anyone else that we know. So we're going to set up 2 possibilities, one in which S contributed, and the other one is the same except for the fact that we replace S with an unknown individual. So we do not make any other changes. We're not going to change the number of contributors between those 2 hypotheses, for example, or not going to state a different type of relatedness between the persons in I and S between the hypotheses. It is actually the easiest to interpret. It's not mathematically forbidden or anything to change several things, but it's easiest to interpret if you just change a single thing between the hypotheses, so that you know that that is actually the thing that caused the evidential value. So the likelihood ratio will then be the ratio between the probabilities of the data that we have under these 2 hypotheses. So either we have HP as contributed, and the persons in I, if any, also contributed. And then we need to explain the data that we have, which are the trace profile and the genotype of the suspect S. And we need to do the same thing under the second hypothesis. So by comparing these 2 probabilities, what we're actually doing is seeing which of these 2 hypotheses has a better explanation for the data. We won't see which hypothesis is true, but we will see which one actually is better able, and to what extent able to explain what has been observed. So now I started out with 2 things that I put in the likelihood ratio that we should predict, namely the trace profile and the profile of the suspect. But actually, we can condition on one, consider that to be given, and then predict the other one. Why can we do that? Because if we would have only the trace profile, and we would have identified the person, let's say on a personal level, but not knowing the DNA profile of that person, then of course we cannot make any statement about then the trace profile is not going to be informative about the contribution. And also the other way around, the profile of S on its own, if we do not yet have the trace profile, is also not going to be informative. So that means that we can consider one as given and try to explain the other one. So then the likelihood ratio can be expressed in 2 different ways, which come out the same, but they give us 2 equivalent ways to express the likelihood ratio and also to think about the likelihood ratio. So on the left-hand side, we have the traditional form where we're going to make a model that predicts the trace, or that explains the trace under HP and HD, and sees which probability is larger than the other one, and that ratio is then the likelihood ratio. But we could equally say that we're going to predict the genotype G of the person of interest that we're having, either assuming that he's a contributor of the mixture or assuming that he's not a contributor to the mixture. So let's look a bit more closely at these two expressions. Then, if we start out with the first one, where we are going to assign a probability to the trace profile under both hypotheses, and in the numerator we have the probability that if a person S with profile G contributes, we would then see this profile M. And in the denominator, we have the probability that if we know the profile of S, but also know that he did not actually contribute, if we then look at the probability of the trace, then we need to compute this, then we get the probability in the denominator. So in the denominator, we're conditioning on the profile of somebody that we know, under that assumption, has actually nothing to do with the case. So that profile is not going to be very influential. We would expect that to be exactly the same had we not known the profile G of S, but because of the way the computations work, with the population genetical models work, it might actually slightly influence it a little bit if we have FST greater than 0. But for practical purposes, and also I think to think about it, it is good to assume that actually it doesn't make any difference. So just to give an idea on why could it possibly make a difference to observe a profile of somebody that has nothing to do with the case? Well, say for example, allele frequencies are estimated from a reference database of persons who have nothing to do with the case at hand. So if we observe a next individual who also has nothing to do with the case at hand, we might actually put that person in our reference database, slightly update our allele frequency database, get new allele probabilities, get new profile probabilities. But of course, they will be almost the same as the ones that we had. So for that reason, I'm just going to pretend that this is not going to make any difference at all. Likewise, if we consider the second expression, then we express the likelihood ratio in another form. We compare the probability of the profile G if it comes from the person S who actually contributed to the mixture that gave trace profile M. And we compare that to the probability to have this profile G of the person of interest if that is a non-contributor. So in the numerator, we have the probability that if we were to see the profile of the contributor that we target with our HP hypothesis, so some models would just target all of the contributors together and say that this is any contributor to the mixture, and other models would specifically target any contributor, for example, saying that this is the major contributor. But whatever we do, in the numerator, we get the probability that if we would see that profile, it would be the profile of the person of interest. And in the denominator, we have the probability that if we just take the probability of this person, the profile of this person S, that it would come out as the profile G that he turns out to have. And that again is going to be almost the same as the population frequency of the profile. Again, for the same reason, it would not always be exactly the same, because the observation of the trace now gives some information about profiles of other individuals, and they again could potentially change the allele probabilities that we currently have. But of course, we're not going to make to use statistical models that actually do too much of that, because we would be in problems if random individuals would disturb the calculations. So what this expression basically amounts to is that it says the probability that the person of interest has profile G, if that person of interest is a contributor, is the product of the likelihood ratio in favor of contribution times the a priori probability, so the population frequency of that profile. And for that reason, of course, we can call what we are doing probabilistic genotyping, because we are actually computing probabilities for a contributor to have a certain genotype. And it's a likelihood ratio that does that for us. So from that point of view, what we want to do is we want to predict the profile of the contributor that we're after. And as long as we have no data on that contributor, for example, when we haven't looked at the trace yet, our knowledge of that profile is expressed by the probabilities for the population at large. So simply by our own population genetic model informed by our own allele frequencies that we have. And then we can use the trace profile M to reduce our uncertainty about the profile of that contributor. So the best thing that can happen, of course, is that we actually get to see that profile. If we would have a beautiful single source profile, we get certainty about the profile of that contributor because you can just read it off. That means that the probability on the left-hand side is equal to 1. We are now certain that this contributor has profile G. Whereas we started out with the population frequency P of G. So that means that the likelihood ratio, of course, has to be 1 divided by the population frequency. And it cannot get any better than that, obviously. There is no way that a mixed profile could suddenly get, that it would be beneficial that the DNA is mixed up with that of other people. So that also implies that the likelihood ratio cannot be more than 1 divided by the population frequency of that profile. So now let me get to the topic of this webinar of today and talk about uncertainty. And I'm going to distinguish between several types of uncertainty that we could reasonably consider potentially problematic, say. The remaining uncertainty about the profile of the contributors, corresponding to how well are they recognizable from the profile, so how well are they resolved. And another different type of uncertainty, how to make the statistical model to do the calculations with. So how do we think that trace profiles arise, and how should we convert that into a statistical model? Which parameters do we choose, and which values do we let them have, and so on? So first, let me start with, well, what could we be uncomfortable about? So I think on good at first sight, when you're used to working with matches or no matches, be a little bit uncomfortable with the fact that it's typically not possible to make a prediction for the profiles of the contributors that have large probabilities in some absolute sense. And at the same time, one can report very strong evidence if one comes across a certain person of interest. Equally, one might be also concerned that there are different models that do not do precisely the same thing, which means that in likelihood ratios obtained on the same comparisons do not have to be precisely the same. But I'm going to explain now that precisely these things actually also occur in a very uncontroversial and long-standing application that I think is quite free of such concerns, namely DNA kinship evaluation. And I'm going to illustrate it mostly with paternity testing or missing persons identification. Because what do we need to do in a kinship case? Well, we have some person that we're interested in, and we have, let's say, a missing person, a person that we target, say. Let's call it a missing person for the purpose of this presentation. And this missing person is sitting in some pedigree, and within that pedigree, we have some genetic data of some persons in that pedigree. For example, of a brother of the missing person, or the parents of the missing person, child of the missing person, or even of the missing person, him or herself. And then we have a person of interest, or say a victim or so, and we want to know, are they the same person? So is this person of interest the missing person? And again, we can do that by setting up a likelihood ratio framework. We're going to compare the possibilities summarized by HP, stating the person of interest is actually the missing person, as opposed to, well, if the person of interest is not a missing person, the person of interest has to be somebody else. And again, by default, we would then take as hypothesis that this person of interest is unrelated to the missing person. So then we have the data on the pedigrees, and we have the profile of the person of interest, D and G, and we need to explain both of them with these hypotheses HP and HD. And again, we can consider one to be given, We don't need to predict it actually. It will cancel out of the equation, so we can consider it to be given and predict the other one. So what we are actually doing then is in that pedigree we have profiles of some persons, and they are going to predict, say, the missing person's profile for us. So we use some relevant information on the missing person, namely the profiles of relatives, or even of the missing person itself, to update, to predict the profiles that this missing person could have. Now, a priori, a person that we know nothing especially about, and we're going to say that that person has a profile G with a priori probability given by the population genetics model and the allele frequencies that we have. So this is going to be our estimate of the population frequency. So that's what we start out with. And then the information in the pedigree makes us revise that probability that we have exactly in the same way as for mixture. So we start out with the a priori probability P of G. We compute the likelihood ratio, and the multiplication of the likelihood ratio with this a priori probability gives us the probability to see profile G given the pedigree. And that's precisely the same thing that we do in mixture analysis. So from that point of view, mixture evaluation and kinship evaluation, they are actually two incarnations of the same problem. And the fact that the profiles are hard to predict, that the profiles of contributors are hard to predict in a mixture, is actually nothing specific to DNA mixture evaluations. We have the same phenomenon with kinship evaluation. So, for example, suppose that we have a father with alleles 15 and 17 and a mother with alleles 20 and 22. Then there can be 4 different children that they might have, corresponding to which allele the father transmits and which allele the mother transmits. So each of those 4 probabilities, the possibilities has probability 1 in 4. So on one locus they may have 4 different children, and if they can have also 4 children on another locus, they may have 16 different children when we look at these 2 loci together. And this number, of course, grows very much when we increase the number of loci. If there are 10 loci, then we easily have 1 million possible children, and if there are 20 loci, that's 1,000 billion. Now, suppose that we have 2 parents and they report their child as missing, and both of those parents are typed on 20 loci. Then that means we cannot predict the profile of that child very accurately anymore, in a sense, because there will be about 10 to the power 12 possible profiles that the child may have. And each of them have about the same probability to be that of the actual child. But at the same time, if we find any of those 10 to the 12 profiles in a person, in a victim, say, then we are very convinced that we've actually found the missing child of those parents. So why are we so convinced of that? Well, again, we need to compare how that victim then got the profile. It may be very hard to predict either way. DNA profiles are difficult to predict simply because there are so very many of them that are possible. So if we look at this person of interest who has one of the profiles that a child possibly can have, well, we know that if that profile could occur as a child profile, and it has a probability of occurrence then about 1 in 10 to the 12. That, of course, isn't very much, but it is way more than the probability that a person unrelated to these parents has that profile. And, of course, it's not a matter of seeing how well we can predict the profile, because we know the profile is there, we have seen it. The question is, how can we explain it in the best way? And that is what the likelihood ratio is telling us. So if that profile of the person of interest has a population frequency, say, probability to occur about 10 to the minus 25 for a random person in the population, and 10 to the minus 12 children, then what matters is how much larger that 10 to the minus 12 is compared to the 10 to the minus 25. So the likelihood ratio will be the ratio of these 2 probabilities, and that's then 10 to the 13. So that's indeed a very large number, even if that profile was actually, in a way, unexpected under both hypotheses. Nobody really saw that coming. That profile was expected with probability 10 to the minus 12 for children, 10 to the minus 25 for unrelated, And that is what matters. So, of course, we would not only get that likelihood ratio for this particular profile, but for all of those 10 to the 12 profiles that could possibly be of a child. But out of those 10 to the 12 profiles, only one of them actually belongs to the missing child. So doesn't that mean that we get many false positives? No, it doesn't mean that, because all of those profiles are actually on their own and also together very rare in a general population. So those 10 to the 12 profiles that we are considering, that is the collection of profiles that could be of a child, is actually quite unlikely that any of them exist in a not extremely large population. We're going to have one false positive per 10 to the 13, so that's 10,000 billion people. And another thing that we observe, in this example, there is no real match between the person of interest and the profile of the missing child, because we don't know what the profile of the missing child has to be. We only have a probabilistic description of it. And that's the same for mixtures. We make a probabilistic description of what the profiles of the contributors can be. So we do not declare a match or a non-match. We are only declaring whether or not there is evidence. And indeed, matches are actually not what we are ultimately interested in. Our task is not to assess whether or not there is a match. It is to assess whether or not there is evidence. And for a long time, it has been a situation that we could only reliably assess whether or not there is evidence in case there is a match. But that doesn't mean that we always have to verify whether or not there is a match, because now we have better models that can just tell us what the evidence is, and we can skip the whole match paradigm. So what can we learn from this kinship analogy? Well, basically, we see that we use all the relevant information that we have. We have the relevant information for the missing person would be the profiles of the parents. And after we've done that, we still have some remaining uncertainty. So in kinship, this uncertainty remains, except when you have the profile of the person, the missing person, him or herself, or of a twin, when you use that as a reference. And for trace profiles, the uncertainty about the contributors remains, except when you have a single source trace observed or derived from the profile. But in itself, the fact that the uncertainty remains is not a concern. What matters is that we correctly interpret all the information that we get, and that we use that to update our opinion. And of course, the more information we have, the better we can resolve this profile that we are actually looking for, so the profile of the missing person and of the mixture contributors. And so we will have fewer false positives. But if you have fewer false positives, it means that the remaining ones necessarily become stronger. So that is the first aspect of uncertainty, the uncertainty about the profile that we're trying to predict. But a second aspect of uncertainty would be the model itself. Because, of course, we are going to have to choose very many things when we want to define a continuous model for the interpretation of peak height. So first of all, of course, we need some kind of probability distribution that predicts peak heights. For example, a gamma distribution or a log normal distribution, or any kind of distribution. We need a degradation model. We need a stutter model. We need to decide which alleles we say are able to stutter. Should they be able to stutter as a -1 or -2 or +1? And what is the peak height distribution of stutters? Will it depend on the length of the allele? Will it depend on the longest uninterrupted sequence and things like that? In addition, we know that there are also sometimes mechanisms at play that generate alleles in a way that is independent from the peaks coming from contributors. So we need to decide on the distribution for those. How many do we expect? What is the variance of how often do we see how many? Is there a maximum number that we think we should allow for in the model? Would we expect these drop-in alleles to come to join in the theta or FFT correction? We need to think about locus-specific amplification maybe, or factors like inhibition and diablees and so on. So there are very many choices to make. And apart from that, what many models do, I'm not sure all of them do, but I think it's quite a common trick, is that they shorten the allelic ladder on each locus. Because that way you reduce to a great extent the number of possible genotypes that you have to consider. Because the number of genotypes on a locus is a quadratic function of the number of alleles that exist on that locus. If you have a locus with k alleles, then the number of genotypes that you can make on that locus is k times k plus 1 divided by 2. So suppose you type a locus which in principle has 20 alleles that occur in the population, and 5 of those alleles are seen in the trace profile. Then if we would not reduce that ladder and work with all those 20 alleles, we're going to have a huge number of genotypes for the unknown contributors. So we start with one unknown contributor, then we do 20 times 21 divided by 2. We have 210 possibilities, and for 2 contributors we have to do 210 times 210, etc. And for 5 contributors, this already runs very much out of hand. But if we say, well, why don't we summarize the unobserved alleles into an artificial allele that summarizes all the others, then we are effectively working with only 6 alleles, namely the ones that we have seen, and the other one that takes the place of all the unobserved ones together. And that enormously reduces the number of profiles that we have to consider, and it makes life much more easy. So as you can see from these numbers, it gives you an enormous reduction already on one locus. And if we do that on all of them, it's even better, of course. But of course, when we introduce, it's not always possible, say, to solve a problem without creating another one. And also in this case, you need to wonder what will happen to the likelihoods of the trace if the unobserved alleles are identified with each other in a single artificial one, which I call Q here. So our first question is, can Q stutter? Is there a Q minus 1? I think that's probably not allowed in the models. And decision is, if you want to have it non-detected, you need to know what fragment length it has. So how many base pairs do we take that Q to be? And if we summarize all the unobserved ones into an allele that cannot stutter, does it mean that an allele cannot have a stutter component anymore if the allele A plus 1 is taken into Q? So for example, if you would have a locus where the largest observed allele was 17, in principle that could have a small contribution as stutter from an 18 that itself was not observed. But 18 is now summarized into Q where Q doesn't stutter. So that possibility doesn't exist anymore. And next question is, people may have heterozygous genotypes for alleles, both of which were not observed, and then they become homozygous for the Q allele. Is it reasonable that we treat them in precisely the same way, disregarding whether they are homozygous or heterozygous in reality? So in other words, if a person of interest has an allele that is not observed in the trace profile, is it relevant which allele that is? That is another question. But next question is, how important is all of that? With this, I just wanted to say that there are very many choices to be made. And in addition, what we should choose, there isn't an obviously logical approach to that. Hardly of them have really a sort of canonical answer, and there isn't any obvious best way to do it. There could be several things that could be reasonably defended as being okay to do. And indeed, in very many cases in practice, it hardly matters which of those particular choices you have made. Especially for a major contributor that stands out, it will not influence the computations at all, which of those choices you have made amongst all the reasonable ones, say. But of course, you could always conceive of some trace profile for which it becomes important. The question is, will you ever get to see any of those? And again, I could make an analogy with kinship when we look at paternity testing. So suppose that I have an alleged father and a child, and I'm testing whether there's a father-child relationship between them. And let's say, for the sake of argument, the mother, I don't have the profile of the mother. So, as I said, this also amounts to predicting the profile of the child, a child that the father could have, and then comparing that to the one of this possible child C that we have seen. Now, with kinship, you take advantage of the fact that DNA is inherited. So we're saying, well, father and child, if there is a true parent-child relation between them, they should share at least one allele on each locus, because the father transmits one of his own alleles to the child. Of course, they could also share both, but that would then be a coincidence. But sometimes, not often, but sometimes there will be a mutation when a father has a child on a certain locus. And if a mutation happens, that may lead to there being no allele being shared anymore. It doesn't have to lead to that, but it may lead to that. For example, if the father would have alleles 16 and 17, and the 16 would be passed on but mutated into 17, then we would never know that a mutation has occurred. But in many cases, of course, the mutation will create some allele that the father didn't have. So, of course, and by a shared allele, I mean that I cannot distinguish them from each other with the technology that I'm using. So alleles that would appear the same to me now with capillary electrophoresis they need not remain the same with NPS, for example. So again, how important is the detailed modeling? So suppose that we ignore the possibility of a mutation, that we just have a Mendelian model saying, well, every parent transmits on every locus one of his or her alleles to a child, always. Well, if that actually happened, or if we do not need mutations, say, if the alleged father and the child share an allele on all loci, then we get a likelihood ratio that doesn't actually differ much from the likelihood ratio that we would have gotten with a mutation model. Why doesn't it make a difference there? That's because the mutations are in themselves rare events, much rarer than a normal transmission, and we don't need any here to explain paternity. But if a mutation has occurred and there is no shared allele, then that will lead us to exclude paternity. So what's the effect of not using a mutation model? Well, it doesn't affect the easy cases, the ones where they still share an allele everywhere, mutations are not, but it does affect the difficult ones, the cases where they do not share an allele everywhere. So that would happen to the actual fathers. What would happen to the non-fathers? Well, not much would change for them whether mutation models are used or not. Of course, if we use a mutation model, and we always allow for the possibility that that there is a mutated allele between parent and child, we still consider that to be a rare event. So we might have more non-fathers that have a likelihood ratio larger than 1, but those likelihood ratios will never be both frequent and large. And as a general rule, that there's a general inequality which is far from being sharp. The probability that the likelihood ratio exceeds x, if the second hypothesis is true, is at most 1 over x. And it is equal to 1 over x only when x is the maximal value that you could obtain with your system. So typically it's actually much less than that. So a likelihood ratio of 10,000 in favor of paternity. You cannot make a model that gives non-fathers probability larger than 1 in 10,000 to reach this likelihood ratio of 10,000. Of course, you need to be aware that also allele frequencies and so on are part of your model. So if you use allele frequencies of the wrong population, then you may actually achieve this. But within the model, if that second description makes good sense as a description of what you do when you randomly sample people from the population, then you cannot make any model that includes many non-fathers strongly as fathers. But again, as with continuous models, we have here very many choices. If we are going to introduce a mutation model, then how should we do that? If a person transmits an allele and it mutates, what happens to that allele? What are the mutants? Are they the original +1? Or could they be also -1, or both of them? Could they also be something else? And what is the probability for each of those possibilities? And does that probability depend on what the original is? I mean, are longer alleles going to tend to get shorter and shorter ones tend to get longer or not? Is that model capable of making alleles that do not yet exist in the reference database? And if so, which ones would that be? Is there a longest to shortest possible allele? And these are similar questions that happen also in mixtures. And here also we can ask, should we want the mutation model to keep the allele frequencies intact over time? Because if there is perhaps no reason that allele frequencies do stay intact over time. But if they do not, then we get already different evidential value depending on in which generation we place individuals. So I said that they're going to be, the point is not that I want you to think about mutation models, but just to realize that in general, statistical modeling involves very many tiny choices. But if you do not need the mutation model, then actually the likelihood ratio is practically independent on which model you have chosen. If you do need them, then the likelihood ratio is going to be more dependent on the choice that you've made. But there is neither in the kinship, neither in the mixture world, a single model that would stand out as being the best one. There are many reasonable choices possible. There's several ones that could make sense. And in most cases, fortunately, it doesn't matter that much which particular choice we make, as long as we acknowledge that the mechanism exists. So in this case, the mechanism that mutation exists, or that the mechanism stutter exists, or that drop-ins exist, etc. So, in a sense, the model contains some leading assumptions and then what I would call more fine-tuning. In mixture interpretation, the leading assumption would be that contributors that put in more DNA, as a consequence of putting in more DNA, they get larger peaks in the trace profile. And we also acknowledge the reality that contributions may differ per person. So we need to make models in which every person may have another contribution. And the difference in contributions should be reflected by us expecting larger peaks to occur for persons who put in more DNA. But it's not only alleles of contributors that lead to peaks being detected. There are also other mechanisms. Some of them are related to the contributors, like stutter, and other ones are not related to the contributors, like drop-in. So we need some fine-tuning to account for the other mechanisms that lead to peaks. And that's analogous to in kinship, where the leading assumption is that we have almost Mendelian inheritance. So a parent will choose a random allele to give to the child, but we need some fine-tuning to account for the occasional non-Mendelian transmission. And the impact of that fine-tuning will depend on the case that you have at hand. Often it is of little impact, but if you make a difference in the model, then it means you can get a different outcome. And if you then subsequently employ a threshold, also you can always imagine a situation where it's on either side of some threshold. But it's better to always be aware of possibilities that sometimes happen than to never take them into account. At the same time, if you could single out, say, easy cases, then you can model more loosely on those. For example, parent-child cases, the easy cases would be the ones where they share an allele everywhere, and there you can afford to forget about the possibility of a mutation. And I think similarly in DNA mixture evaluations, if you have a very prominent contributor standing out, then the stutter model is not going to be of much importance for that contributor. So by analogy, it's reasonable to expect that for the easy cases, the likelihood ratio will be highly similar for all mixture evaluation models that comply with these basic assumptions. So that they all acknowledge the fact contributors may have different relative contributions and that the peak heights reflect that. So when is a case harder? Well, when it's difficult to differentiate between contributors because they have equal mixing proportions. So that affects those contributors that are equally mixed up with some other ones. It doesn't necessarily have to affect all the contributors. And of course, cases are also going to be harder if we are going to compare a person of interest with peaks in the profile that need not even be actual alleles. Then the likelihood ratio has opportunity to depend strongly on the chosen model, but in general, it will also be a smaller likelihood ratio. it just acknowledges the fact that this is a more difficult comparison and that we have less certainty on what we're actually looking at. Same as with parent and child duos that need mutations to explain paternity, then you also get weaker evidence. But what you do not want is to categorically rule things out that can sometimes happen. So the question then is, how far should you want to go in the modeling? And that primarily depends on how far do you want to go with your model. Do you want to go after all the minor contributors? Then you have to be very specific in the model. So a last thing that I want to discuss is what if we make, so how important is the quality of the model for the true and false positives, say? Well, as long as we make a model that doesn't use the profile of the person of interest, let's say that doesn't know who the suspect is, without the knowledge of the suspect, it's impossible to introduce bias against a suspect. So that means that you cannot have very many unrelated non-contributors with strong likelihood ratios in favor of being included. Whatever you do, that doesn't depend on the quality of the modeling. That is just something that cannot happen. So the quality of the statistical model actually is much more reflected by the extent to which you will find evidence against actual contributors, about people who really put in DNA. And the effect of poor or unrealistic modeling is in the first place that you lose the evidential value against actual contributors. So you're going to be conservative. And it could be even so conservative that you just don't see that there is evidence at all anymore. Whereas the false positives, well, precisely which profiles would lead to, say, false positives, that depends on the model. That set will change, but it is impossible to find many and strong at the same time. But even if you have the model in place, then you need to think about parameters in that model. For example, the mixing proportion, peak height expectations, number of contributors, etc. If we would know their value, we could do the computations, but we don't know their value generally. So we need to think about how we are going to give them a value, say. So there are two standard tricks, basically, and one is, say, use only one value, and the second is use many values. And the use only one value would be that you plug in some value, and then, of course, it makes sense to take the value that best explains the profile that you have. So that is called the maximum likelihood method. You are going to let the parameter vary and see how well you can explain the trace then. And when you can explain it best, you say, okay, I'm going to take that parameter value. Whereas the second approach would be that you say, well, this parameter could be in a certain range, but then you have to specify with which probability it takes which value in order to come up with a single number as likelihood ratio. So when would you do which approach? Well, it could be that we have a fairly good idea of which values of the parameters we need to take, and then all we need to do is implement that. So one example of that is actually the genotypes of the unknown contributors. We could also consider them to be model parameters in a way. If we would know all the contributors, we could predict the trace's profile, and if we don't know them, we just have to try out all the possibilities and then weigh those with the allele frequencies that we consider to be known. And so if we think that these allele frequencies are a good description of the population that we're looking at, then we will work with that distribution. We wouldn't do maximum likelihood to assign, say, maximum likelihood profile. Summing over the genotypes is then the right thing to do, that uses all the knowledge that we have. But sometimes we don't have any knowledge, we're uncertain about what to do with that parameter values, and then it's tempting to just take a computationally convenient distribution, or for one that makes the computer work faster or better, one that has attractive properties, but that does not necessarily reflect any realistic modeling assumption. And of course, then you need to check whether that choice will matter much. And an example of that would be prior probabilities for the number of contributors, for probabilities of dropout of peak heights, etc. So then again, you have to decide whether you work with range or with a single number. And maximum likelihood in practice actually is quite often a satisfactory solution. But it is a little bit more vulnerable since you boil it down to using a single number for those parameter values. So the last thing that I want to look at, so suppose we have two models and they give a different likelihood ratio. What should we be concerned about that? Should we want to look into that? So our first example is one we basically should not, is if we compare, say, a discrete model with a continuous model. A discrete model is one that only looks at the alleles in the trace and ignores or doesn't get to know what the peak heights are. And a continuous model is one that is going to use peak heights, of course. Now, of course, if you take more relevant data into account, you're going to be able to better answer the questions. And that, in this case, means that the continuous models are going to give you likelihood ratios that separate better between contributors and non-contributors. So if you see a true contributor, you'll recognize it more strongly, say, with a stronger likelihood ratio. And you're also better at not finding evidence if there isn't any. So that means that some profiles that give you some evidence in favor of contribution with the discrete model no longer do so with the continuous model. But that doesn't mean that discrete models lead to too many false positives. And again, that is something that you could also illustrate with kinship analogy. So I need to have two evaluations, one that uses more information than the other one to compare it to the discrete and the continuous methods. So for the discrete method, I would say I would do paternity testing only with the alleged father. And a continuous model is given access to more relevant data, namely the profile of the mother of the child as well. So if I include the mother in the comparison, then I'm going to get a larger likelihood ratios for the actual father. And exactly as with the discrete model, there will exist profiles, not necessarily persons, but there will exist profiles that could be the father's profile in the absence of the profile of the mother. But then when you get to see the profile of the mother, they no longer can be. But that cannot happen often. You can give bounds as to how often that can happen. And it certainly doesn't invalidate the first method. It just, both methods use whatever information they are given to reduce the uncertainty with that information. Both of those are functioning correctly, but they cannot come up with the same answer because they, at least not always, because they're not given the same information. But what if two continuous models have a difference in opinion? Because obviously, if we have the same data that are fed into the computer, we would be happy if they give the same results each time, because you give them the same input, you would like to have the same output. Now, of course, these models are not precisely the same, and different modeling specifications gives at least theoretical opportunity for results to differ, to be not numerically exactly equal. But at the same time, we expect the agreement should be better as the likelihood ratio is larger, because a larger likelihood ratio means that you've been able to resolve that contributor well. And if one model is able to do that, it makes sense to think that the other models will also be able to do that. But for more difficult minor contributors, there may be more opportunity for differences because the likelihood ratio is simply going to be more model dependent. So I don't think there's a very easy answer to what to do if they differ in opinion. I think there is no general rule to be given here. I would say we would scrutinize the assumptions that each of them makes and see if they are particular importance of that, in that case, at hand. At the same time, we have to also keep in mind strong false positives are generally less likely than false negatives, because strong false positives are very hard to make, whereas false negatives are much easier to make. So that concludes the presentation for today. So as has been mentioned in the introduction, Ronald Meester and I are writing a book which now has the sort of preliminary title Theory and Philosophy of Statistical Evidence in Forensic Science, which will appear next year under a title similar to this one. And the material that I've been showing today will also be taken into that book and perhaps also in another publication. Anyway, thank you very much for your attention, and I will try to stop sharing the screen now.
Okay, thank you so much, Klaus, for an excellent presentation this morning, and we will definitely continue to look for your writings on these matters. Thank you so much for helping us with today's webinar. And with that, I would like to invite our next speaker, Dr. Khalid, to begin sharing her screen, and feel free to begin your presentation when you're ready. Thank you so much.
Thank you for the introduction. I hope you're able to see my screen now and you can hear me clearly now. So I will give a talk about another topic of uncertainty, and that is the problem with not knowing the number of contributors. And this topic has already turned up quite a lot of times in the previous webinar because it's one of the major uncertainties in DNA evaluation. Okay, so we will look a little bit more detail into that now. So my talk is roughly structured in 3 parts. So first, I will give some introduction with some hat example, as you will see soon. Okay, can you see my screen now? I hope.
Yes, we have your slides, yes.
Okay, so I'll try to move on now, some slight technical issues. Okay, so I'll start with the introduction, and after that there will kind of a little bit of theoretical section, so giving you some background about why that we have this problem with a number of contributors and what is it due to. So there will also be some formulas, some equations, but I'll explain them very slowly and also have lots of examples. So I hope that you will get some good background information from that. And after that, in the third part, which is the largest one, I'll give you some practical issues about how to deal with this problem about not knowing the number of contributors. Okay, so let's start with the first one, with the introduction. Okay, and I'll start with an introductory example, which I call the hat example. So this is a very simple example, which illustrates, hopefully, the idea about the number of contributors nicely. So this example here is from a paper here from Biedermann, Taroni, and Thompson 2011, where this was put as an example. Okay, the example goes in this way. We have a criminal, in this case a murderer, where we know that this criminal wore a hat. This is known by a surveillance camera. And then we found a mixed DNA stain on that hat, and we know nothing whatsoever about the number of contributors. You see here in this table the crime stain, which is found here, and the alleles which correspond to that. As you see, we have a very simple profile of 7 loci, and you see that most of them have 3 alleles, but you can also see that we have this here, FGA, and also the other 2 here have 4 alleles. Okay, so what is the number of contributors which you would assume? So one possibility would be, of course, to have 2 contributors. But later a suspect was found, and this here on the right side is then his genotype profile. And you can see that for these 2 loci here, we have got homozygous genotype, which means because we have here 4 alleles here on the crime stain, it's no longer possible to have 2 contributors and include the suspect. So if you want to include the suspect, you must have at least 3 contributors. Okay, therefore the suspect would be excluded if we had only 2 contributors. So what shall we do? Shall we just go with 2 and exclude the suspect, or shall we simply choose 3 and calculate the maximum the likelihood ratio for these 3? Okay, so we'll return to that example later. This is kind of the usual slide with likelihood ratios. We've already seen it before in Klaus Slotin's presentation. So this is just to to remind you and also to give you an introduction to my notation here, that we have some data D, which consists of our mixture profile M and also of the profile of the person of interest. And we have also the usual hypothesis. So H1 is that a person of interest is a contributor to the mixture, whereas H2 is that the person of interest is not. Okay, then we can write down the likelihood ratio in this way. So it's the probability of the data given H1 divided by the probability of the data given H2. We've seen in the previous presentation that there are also some equivalent ways about writing that down. So this is one of the simplest, so I'll stick to that. If you now want to calculate the likelihood ratio, this is not so easy to do it straightforwardly. Why is that so? Because H1 and H2 are at the moment not sufficiently specified. For example, we do not know what number of contributors to take for H1 and for H2. And we will now at the moment only focus on the number of contributors. So one question which has arisen is whether the number of contributors is the same for H1 and for HP here, as you see on the left side here, or whether we should choose different number of contributors. So let's look at the hat example. So which number of contributors could you choose for the hat example I just showed you? So if you were to go with the same number of contributors, then we have kind of two possibilities. So either we can take 3 contributors under H1 and under H2. So then for H1 we would have the suspect and 2 unknowns, and for H2 we would have 3 unknowns. Or we could have 2 contributors, then for H1 the suspect and an unknown, and for H2 2 unknowns. The other possibility is then to have different numbers of contributors. In this case, we could, for example, take 3 contributors under H1, because if we take 2 contributors under H1, so this would result in a likelihood of 0 here. Therefore, we would usually choose 3 for that. So we have the suspect and 2 unknowns. And we could perhaps choose then for H2 2 contributors. So here we would then have different number of contributors for H1 and H2. Okay, so now this question isn't completely agreed upon at the moment, and it was also discussed in a letter by Hoshutini and Egeland in 2016 in FSI Genetics, and they argued for the case to have the same number of contributors. So, and here are some arguments for having the same number of contributors. What they say is that if the difference between H1 and H2 is more than the inclusion of the person of interest, for example, if you have also different number of contributors, then it is not clear to which changes the likelihood ratio is due. So is it due to the inclusion of the person of interest, or is it perhaps due to a different number of contributors? Therefore, they argue that the presence or absence of the person of interest should be the only difference between the hypotheses. And if, for example, you cannot agree on the parameters, so if you cannot agree on the number of contributors to choose, then you should compute different likelihood ratios for different parameter values. So, for example, for different number of contributors, but you should choose the same number of contributors for H1 and H2. Okay, so what are the arguments for not having the same number of contributors in H1 and H2? So, for example, in the ISFG recommendations 2006 here, they said we could also have different number of contributors. And then in reply to the letter I just told you about, Hoshutini and the Egeland, there was, well, furious replies here from Peter Gill, Charles Brenner, and Ian Abbott about this matter, and they argue that you should not have the same number. So there are many arguments put forward for that. I'll just show you here those which are kind of the most sensible ones and the most important ones. The first one is that there might be actually cases where the number of contributors might be different for prosecution and defense because you have different setups in these situations. Then the second argument is that each party, so prosecution and defense, should be able to adapt the number of contributors to their specific scenarios and to their specific wants. And this may well lead to different choices of the number of contributors and also of other parameters, which we will not talk about now. So let's look again at the head example, what this means for this case here. So now suppose we have different number of contributors for H1 and for H2. So the usual choice would here have 3 contributors for H1 and 2 contributors for H2. Now assume that we calculate then a large likelihood ratio. Then, as Protottini and Egeland argue, we do not know what the cause is for this large likelihood ratio, because there are 2 possible reasons. Either it is because the suspect is a contributor, and therefore we have a large likelihood ratio, or it might be that he's not a contributor, but that 3 persons fit the data much better than 2. Then we would also get a likelihood ratio. And by looking only at the likelihood ratio, we do not know which cause is the true one. Okay, so this was introduction why this is important and also some example, and we will later come back to this head example. Now some theoretical background. First, I'll start with another example. I'll call that the gun example, and the gun example consists of 2 scenarios. So let's now start with the first scenario, scenario 1. So in this scenario, a gun is found at the crime scene and we find a mixture trace on the gun. We are now only in the investigative phase, so we do not have any information about the case at the moment. There's no prosecution and defense, also no suspect. So what we are only interested in at that moment is, has a certain person of interest contributed? Okay, so in this scenario, H1 and H2 are quite straightforward. So H1 is the person of interest and unknown and perhaps other unknown unrelated persons contributed, and H2 is that only unknown unrelated persons contributed. So with respect to the number of contributors, in this case the number of contributors is at the moment completely unknown, and even if we were somehow to know the number of contributors, this wouldn't help us to decide whether we have evidence for H1 or H2. So this is the first scenario where we have really little information. And let's contrast that to the next scenario, which I will call scenario 2. Again, we have a gun. A gun is used in a crime again, but now we have a lot of information. We know that 2 persons, I will call them K1 and K2, handle the gun. And the question is now, has a certain suspect additionally handled the gun? And we have here, we suppose here that we have very specific hypothesis, because we have also very specific information. So H1 is now that we have only 3 persons who had handled the gun, and these were K1, K2, and S. So this is kind of this scenario here on the left side. So we have here the suspect, S, and K1 and K2, which handled the gun, and we are sure that nobody else handled it. So for H2, we know that only K1 and K2 handled the gun here on the left side here. K1 and K2 handled the gun, S handled not the gun. So in this case, we have 2 contributors. As you can see, the number of contributors is either 2 for H2 here, or it is 3 for H1. And as you can see here, if we know now the number of contributors, we will automatically know whether H1 or H2 is true. So as opposed with the previous scenario, we know here very exactly, or not very exactly, but we know that the number of contributors can be only 2 or 3. So we have much information about the number of contributors. And also, if we know the number of contributors, this will also give us information about H1 and H2. Yes, we will come back to this example later. Yeah, but first we have to look at the concept of nuisance parameters. So in statistical models, you have usually 2 kinds of parameters. So the ones which are most important for application are the so-called parameters of interest. So these are the parameters you are really interested in, which you want to estimate or to test. So for forensic questions, these are usually the hypothesis H1 and H2. What we want to know here in the setup I've just shown you is it H1 what is true, or is it H2 what is true? So do we have evidence for one of them? Then it is, of course, difficult to calculate that directly. You need a model for that. And for this model, you need a lot of additional parameters. Because you're not really interested in these parameters, but you still need them for modeling and for calculation. These are called nuisance parameters. We have seen a lot of these parameters pop up during this webinar. So, for example, probabilities of drop-in, probabilities of stutter, parameters of peak height distribution, and lots more. So in this presentation here, we are only interested in one of these nuisance parameters, and that is the number of contributors. So it's important to notice that the number of contributors is not something we are interested in per se, but we are only interested in so much in it as that can help us to evaluate our hypothesis H1 or H2. So we are only interested whether the person of interest or a suspect has contributed, but we are not really interested how many other persons have contributed. So the number of contributors is also a nuisance parameter which we need for our calculations, but which we do not need for arriving at some evidence for H1 or H2. Okay, and now this is the slide where one of the formulas appears. How do we do that? So we have the number of contributors, and we're really usually not sure what is the correct number of contributors. So if you then want to calculate the likelihood ratio, we have several possibilities. And what we usually do then to arrive at an overall likelihood or at an overall likelihood ratio is to calculate the likelihoods for all of these possibilities which are plausible, and then get a weighted likelihood ratio or an averaged likelihood ratio. Let's see this slide here. So this is the likelihood for H1 or for HP. So that's the probability of the data given H1 or H2. For that, we have to calculate the likelihood here. This is this term here, given we have a certain number of contributors. So we have certain possibilities for the number of contributors, let's say from 1 to some maximal value, which we find plausible. And then we calculate here the likelihood ratio for all of these possibilities, n number of contributors. And then we calculate an average, which is then weighted also by the probability that we actually have n number of contributors from a given H1 or H2. So we calculate the likelihood given n contributors times the probability of having these number of contributors. So this is then a weighted likelihood. Here, this is just another way to write that down, because this is a likelihood given n contributors, so we can also write that ln of H1 or H2. As you can see, we need for that the probability of having n contributors under H1 or H2. These are so-called prior probability of the number of contributors under H1, H2. And these are the probabilities of having a certain number of contributors without the genetic data. So these you can, for example, get from some case information. For example, from witnesses, where you say, well, we have so and so many people, from cameras, and also from other case relevant information. But you're not allowed to take genetical data into account, but just prior probabilities before looking at the genetical data. And as you can imagine, these are often difficult to determine. And especially important it is to know, are the probabilities for the number of contributors, are they the same given H1 and given H2? So this might be the case and might also not be the case. I will term that equal NOC probabilities, so equal probabilities for the number of contributors. So if we have now the case that the same number of contributors are possible for H1 and H2, although with different NOC probabilities, then we can calculate an overall likelihood ratio. And this is, in the vast majority of cases, the case. So this is quite a very sensible assumption to make. So then we can see, similar as before, that the likelihood ratio is the likelihood ratio given n contributors for H1 and H2 times the prior probabilities for having n contributors given the data at H2, and also the prior probabilities having n contributors given H1 divided by n contributors given H2. Okay, so, and if we assume equal NOC probabilities, so the same probabilities of the number of contributors, then you can see these two here cancel out, and we get here an equation which is perhaps a little bit easier, but which is also very important. So the overall likelihood ratio, as you can see then, is again a weighted likelihood ratio. It is the likelihood ratio for n contributors in H1 and H2 multiplied by the probability that you have n contributors when looking at your data and when assuming that the person of interest has not contributed. So this is a kind of key formula, and we will see an example for that presently. So as I already told you, that is weighted likelihood ratios, but what is important now is that we here use only likelihood ratios with the number of contributors equal in H1 and H2. So what you should do is then you should calculate several likelihood ratios for several possible number of contributors n. And if you're lucky, they wouldn't differ so much. Okay, so now let's look at an example. We will again use the gun example. In scenario 1, so you might remember that's in the investigative phase, so we have not much information about the number of contributors, and we can assume that the number of contributors has about the same probability under H1 and H2. That means that we can have this equation which we've just seen, so we have that the overall likelihood ratio is a weighted likelihood ratio over the likelihood ratios for a given number of contributors and weighted by the probability that the number of contributors is n given D and H2. So in this case, we have only to mind about likelihood ratios with the same number of contributors in H1 and HD. So this is kind of the first answer to the question, shall we take the same number of contributors or shall we take different ones? Now let's look at scenario 2. We have seen that scenario 2 was quite different. Why was that so? Because then in H1, we always had 3 contributors, K1, K2, and S. Whereas for H2, we had only 2 contributors, K1 and K2. This means that the probability of having 2 contributors under H1 was 0 because we only have 3 contributors, and therefore the probability of having 3 contributors here is 1. It's just the other way around for H2. For H2, the probability of having 2 contributors is 1, and therefore the probability of having 3 contributors must be 0. That means if we look at H1 here, then the likelihood of H1 is simply the likelihood considering only 3 contributors, because the other probabilities are all 0. If we look at H2, then the likelihood for H2 is the likelihood for 2 contributors under H2. And therefore, the likelihood ratio, as you can see here, is the likelihood for 3 contributors for H1 divided by the likelihood for 2 contributors for H2. And therefore, you see here, we have here different number of contributors for H1 and H2. And you can see here, therefore, that both is possible. So it's possible that we have only to regard the same number of contributors here, or that we have different number of contributors. And I will show you later in the practical implications how to deal with that in practical situations. Okay, let's now consider a case which happens quite frequently, and that is that you have a trace and you're not sure do you have 2 or 3 contributors. There we have only these 2 possibilities, 2 or 3 contributors, and then the formula which you've seen before for equal NOC probability gets a little bit easier. So then the overall likelihood ratio is the likelihood ratio for 2 contributors times the probability of having these 2 contributors given the data and H2 times the likelihood ratio for 3 contributors times again the probability of having these 3 contributors given the data and that the person of interest has not contributed. So now it may happen as we have seen in our hat example, that if you have 2 contributors, then the likelihood ratio is about 0 because the suspect cannot be fitted to the data if you have only 2 contributors. It might also happen, but that LR3 is large. What does it mean to our equation we have here? That means LR2 is 0, and therefore all the first summoned here is 0, and therefore simplifies to this. So then the likelihood ratio is simply the likelihood ratio for 3 contributors times the probability of having 3 contributors when looking at the data and when assuming that the person of interest has not contributed. Okay, so this seems in this case quite easy. So we have only to calculate the likelihood ratio for 3 contributors, but then we have this weighting factor here. So this is a probability, so it can of course be between 0 and 1. If it's 1, so that's fine, because then we have LR for 3 contributors. But if it's 0, the overall likelihood ratio would also be 0. So we have kind of take care of this factor. Okay, and the problem is when this factor here is small, because when this factor is small, the overall likelihood ratio is also small. And this is small only if 2 conditions, or if one of 2 conditions is satisfied. So on the one hand, this is the case if data are much more likely for 2 than 3 contributors. You can imagine the probability of having 3 contributors when given the data, that this is very small if the data are much more likely for 2 than 3 contributors. So if you look at your profile and you're really sure that you have 2 contributors and not 3, so then this probability might get very low. So this is one possibility. The other possibility is that if you know that 2 contributors are much more likely than 3 contributors a priori, for example, if the case circumstances are such that if they really support 2 contributors, then also the probability of having 3 contributors here given H2 and given the data is of course also very low. And then it might be that the overall likelihood ratio might be far from the likelihood ratio for 3 contributors. Okay, this is a little bit theoretical, so we'll look at an example here on the next slide here, and again the hat example. Perhaps you will have noticed that for the hat example, we have exactly that case. Okay, so here are the likelihood ratios calculated for each locus. Here assuming in this column here, assuming 2 contributors, and in the other column here, assuming 3 contributors. If you have 2 contributors, we have already seen that for these 2 loci, because we had homozygous genotypes there for the suspect, they produce a likelihood ratio therefore of 0 because the suspect cannot be fitted to the data. So we have here for these 2 loci likelihood ratio of 0, and which means that we have of course also an overall likelihood ratio of 0. If we assume 3 contributors, we have no longer a 0 because now the suspect could fit the data. And if we then calculate the overall likelihood ratio, this will be a likelihood ratio of about 10,000. And you can see here we have exactly the case that if you have 2 contributors, we have a likelihood ratio of 0. If you have 3 contributors, you have at least not a very small likelihood ratio. So which number should you take? Should you take the 0 or the 10,000? We have again our formula which we saw just before. The overall likelihood ratio is now consisting of 2 components. First, the likelihood ratio of 3 contributors, which is 10,000 in this case, and then the probability of having 3 contributors when looking at the data and assuming that the person of interest is not included. Okay, so here are some numbers of how the likelihood ratio might change. So if the probability of having 3 contributors under these conditions is a half, 0.5, then of course also the likelihood ratio is also a half because we simply multiply that. If we have that the probability of having 3 contributors looking at the data is only 10%, then the likelihood ratio is also only 10% of our original value. And if this probability is even lower here at 0.01 or 1%, then the likelihood ratio goes down from 10,000 here to 100. Okay, now let's again think of our hat example. Here we know a little bit about the circumstances of the case. And I just told you when it is possible that we have here a small value of that factor here. Okay, and we know it is small if either of the following conditions are satisfied, either if the data are much more likely for 2 than for 3 contributors. So let's look at the data we have and see whether they are much more likely for 2 than for 3 contributors. And actually, we can calculate that here. So we can calculate with the alleles we have the probability for the data for 3 contributors divided by the probability of the data for given 2 contributors under H2 is 2.27. And as you can see here, the likelihood ratio is slightly in favor of 3 contributors. Therefore, what you can say here is that the data is not much more likely for 2 than for 3 contributors. So this is not valid here. So the other problem would be that if 2 contributors are much more likely than 3 contributors a priori. So if we know by the case circumstances that we kind of nearly only could have 2 contributors. In our case, what we have here, we know that we have got a hat. So we have a hat which may lie around, which a lot of people may handle and whatever. So in this case, we cannot say that kind of 3 contributors are very unlikely, because it might quite easily happen that 3 contributors contributed to the sustain. So in this case, we also couldn't say that 3 contributors are much more likely than that 2 contributors are much more likely than 3 contributors, because for a hat that is, if we know the circumstances now, this can easily be the case that the hat is handled by more than 2 persons. So I'd say this is also not satisfied for this hat example. Okay, that means this wouldn't get very small, which is kind of a good news for us. That means we don't have here to look at very small values. So one possibility would be that, for example, if we take this as a half, which would be conservative estimate, then we would get kind of a likelihood ratio of about a 5,000, and this might be kind of a good conservative estimate. Okay, so far for the theoretical part. Now I'll come to the more practical considerations about what to do when actually having a trace here. Okay, in general, here's some general points which to take into account. So actually, we need to know the number of contributors under H1 and under H2, or the probabilities for the number of contributors, the prior probabilities of the NOCs under H1 and H2, to calculate the exact likelihood ratio. But these are usually very difficult to determine, so we have to resort to other means. The second point is perhaps rather obvious. Nevertheless, I'd like to stress that because it is not possible to determine the number of contributors without uncertainty, and especially if you consider probabilistic genotyping, because then you always have the possibility of having low contributions. If we look at the hat example, there might, of course, always be some minor contributors contributing to the stain. So we're not really sure about the number of contributors with any certainty. And of course, there might also be artifacts which might either mask or pretend contributors. So a point which has already been addressed in the webinar before is that the processing of the data might influence the assessment of the number of contributors. For example, the threshold for filtering noise or artifact filtering might affect the number of contributors and the assessment of the number. Okay, so this were some general points. Now I come to some specific issues here. So first, let us again look at the question, number of contributors. Should we choose the same one for H1 and for HP? So we have seen on the previous slide that both is possible. So if both hypotheses hold the same number of contributors to be possible, then the likelihood ratio is a weighted average of the likelihood ratios for the same number of contributors in H1 and H2. 2. And we have seen that, for example, in scenario 1 in the gun example. Then all number of contributors are possible the same for H1 and also for H2. But if that's not possible, so if we have a certain contributor number which is possible only for one of the hypotheses and not for the other, then different number of contributors can be used. So this was the scenario 1 for the gun example, where we have for H1 3 contributors, K1, K2, and S, and for H2 only 2 contributors, K1 and K2, and then the likelihood ratio, of course, looks like this. So we have then for H1 3 contributors and divided by the likelihood ratio for 2 contributors. So this might be a little bit of a problem that both are possible, but well, let's take a more detailed look at this scenario 2. So, and if you again consider scenario 2, you will probably also find out that this is a very specific example, and I would even term that an artificial example. So H1, we say only K1, K2, and S handle the gun. Those are 3 contributors then. But it, of course, might also be possible that we have only the contributions of K1 and S, or K2 and S. So these would also be realistic setups here for H1. So for H1, it's not important that K1, K2, and S handle the gun, but it's only important that S handle the gun. And if we cannot find traces of either K1 or K2, but of S, so this would also be possible. So in this case, 2 contributors or even 1 contributor when only S handled the gun would also be sensible options for H1. And if you look at H2, here the scenario was that only K1 and K2 handled the gun, so limiting the number of contributors to 2. But of course, why shouldn't an additional unknown have handled the gun so that 3 contributors would be possible? So as you can see, if we have realistic options here, usually we have the same number of contributors possible for H1 and H2, except in very, let's say, very, very specified, specific examples. And also, on the other hand, if you insist on a fixed number of contributors, like for example here 3 for H1 or 2 for H2, so then you make the opposite hypothesis provable, so that weakens one position and so not a sensible option to do. Altogether, this means that only very rarely are likelihood ratios with different number of contributors relevant. I wouldn't say never, but I think for practical circumstances, it is a very good option to concentrate on number of contributors with the same number of contributors for H1 and H2. So this is what you have to calculate. So next, I want to look at a method which is often used for estimating the number of contributors, this so-called maximum allele count method. I think most of you have already encountered this method here. So it's a very simple method. You look at the number of allele peaks, count them per locus, and divide it by 2 and round it up. And this results then the minimum number of contributors required. Of course, before you count the number of allele peaks, you have to remove all the additional peaks which are not caused by the alleles. So it requires filtering of noise and stutter peaks and other artifacts first. As you can see, this results in the minimal number of contributors, and therefore it's of course an underestimation of the number of contributors. And this is especially problematic if you have large dropout. Nevertheless, it's still widely used in practice. So let's look again at the hat example. So if we look at the crime stain here, you see here then the maximum number of alleles is 4 for 3 loci here. So we would divide 4 by 2, which is 2 then. So the number of contributors according to this maximum allele count is then 2, which would then mean that the suspect is always included. As you can see here, this is quite an unreliable method. Okay, I now want to stress some points which are specific to continuous models, to probabilistic genotyping. So one of the main advantages of probabilistic genotyping is that contributors are not either fully there or fully not there, but you can have kind of fractional contributors. So what I mean by that is that you have major contributors, minor contributors, you have different mixture proportions. And because that is so, it means that the number of contributors is kind of overestimated. You have kind of additional artificial contributors, then they can be said to have near zero contribution, so they kind of fall out of the picture, which means that this doesn't disturb the likelihood ratio calculation much. So this is really a very good benefit of the probabilistic genotyping methods. Another point is if the person of interest is not the major contributor, but only the kth major contributor, then of course it can only be modeled if the number of contributors is larger or equal to k. If it's smaller than k, then of course the kth major contributor cannot be fitted, and therefore it will be lost. Yeah, we can see that nicely from the data from a paper by Taylor 2014. You see here in the first column is the DNA concentration, 450 picograms, and here in the next two columns here, see the contributors, the true contributors, which were in this mixture. You see here we have two contributors. This is contributor 1, this is contributor 2, and you see here then the proportion, the mixture. So, for example, in the first line, both are in equal contributions, 0.5 and 0.5, and if you go a little bit further down, you have 0.2, 0.8, and then 0.09 for the first contributor and 0.91. Here in the next two columns, you see the estimated mixture proportions when analyzing it with a model using the true number of contributors, which is 2. And you see that the mixture proportions are quite nicely recovered, sometimes a little bit better, sometimes a little bit worse. Of interest are here the last two columns. This is when we model it not with 2 contributors, according to the true number of contributors, but with 3 contributors. So we assume an extra contributor which is actually not there. And what you see here is then that the third contributor will get a very low contribution here. You see here the first and the second contributor get here now a contribution of 0.49 instead of the true values of 0.5. And the third artificial contributor gets a very low proportion of 0.02. And this is, as you can see here, for nearly all of these setups the case. So this is really what I told you before, that if you have an artificial contributor, this is usually modeled as having a very low contribution and therefore doesn't play a strong role anymore. I will now focus on 2 errors which might happen if you look at the number of contributors, and the first one is overestimating the number of contributors. The second one is underestimating the number of contributors. Let's first start with overestimating the number of contributors. For continuous models or probabilistic genotyping, the likelihood ratio does not change much if we have overestimation of the number of contributors, because, as we've seen before, the additional artificial contributors are usually set to near zero contribution. And therefore, if we look at contributors, real contributors, I mean by that, then the likelihood ratio for contributors decreases then a little bit because we have, of course, more noise in the data. If we look at non-contributors, there the likelihood ratio increases because we have more contributors now. We have more possibilities for non-contributors to fit to the data. And therefore, usually the likelihood ratio for non-contributors get less exclusionary, but mostly they do not get to falsely incriminating, but they usually go to incisive, to the region where we really cannot make a decision, neither support H1 nor H2. Let's look here at some examples. So for the last time, the hat example, we have already seen that for 2 contributors, we have a likelihood ratio of 0. And if we assume 3 contributors, we have also seen that we then get a likelihood ratio of roughly 10,000. If we now increase the number of contributors one further to 4, then we also get a likelihood ratio of roughly 1,000. You see, it doesn't change so much, although this is not a probabilistic genotyping approach, but a discrete model. But now we come to some continuous models here. So this is from the PCAST response, Bright et al. 2018. This was calculated with StarMix, and here we have the results for contributors. So let me now first tell you what these pictures are about. Here on the left side here of the picture, we have the number of true contributors is 3. For the x-axis, this true number, is also assumed by the model. So we have 3 contributors, and we also assume 3 by the model. Whereas here on the y-axis we have again 3 contributors, 3 true contributors, but we assume 1 more. So we overestimate the number of contributors by taking here 4 contributors. What you can see here is that a lot of these points are on the diagonal line, which means that they give the same log likelihood ratio here, but you see that also some points are slightly lower the diagonal line, which means that if we assume an additional number of contributor, then the likelihood ratio decreases a little bit. We get lower likelihood ratios if we assume too many contributors. We have roughly the same here on the right side. We have here 4 true contributors, and we have here on the x-axis again 4 contributors assumed by the model, and here on the y-axis we assume 1 more, and we see again that the likelihood ratio is it corresponds quite good here, but the likelihood ratio is a little bit lowered if we assume 1 contributor too many. So this is for contributors, and we see here also some similar plots here. This is from Bleeker et al. 2017 for Euroformics. Here we always assume that the number of true contributors is 2, and here on the x-axis we again assume also with the model the same number of contributors as the true ones, so we assume 2 here, and here we have the likelihood ratio under that assumption, and on the y-axis we assume more contributors, so we assume here 3 contributors, 4 or 5. And we see here also a very good correspondence in the model. Okay, so this is again for contributors, and on the next slide I want to compare contributors and non-contributors here. This is again from Taylor 2014 here. Here now this picture is a little bit different. You see here now on the x-axis the DNA concentration is here on the x-axis, whereas on the y-axis we have the log likelihood ratio, and we assume a true number of contributors of 2. Okay, so H1 contributors are the 2 blue lines here. The upper blue line here is for the true number of contributors, 2, and the lower blue line is for 1 more, so for 3 contributors assumed by the model. And you see here that for high concentration, the 2 models agree, but for lower concentration of the DNA, we see that the likelihood ratio is a little bit lower for true contributors. So this corresponds to what we have just seen before, but what we haven't seen is how the likelihood ratio behaves for non-contributors, so under H2. So here we have 2 red lines. Again, the red line for the true number of contributors assumed by the model, so that's the lower red line here, and you see that has got a log likelihood ratio of about -30, so this is exclusionary, and we see that it gets a little bit higher if we assume 1 contributor too many. So this is the upper red line. But what is perhaps more important is that we have here these red points here, and you see here these red points mean that if you assume 1 contributor too many, then non-contributors can get a likelihood ratio which is no longer exclusionary, but which is kind of more in this inconclusive range. But you see also that it is not in the range that it is incriminating. So this is one part of the coin. So now let's look at the other one, underestimating the number of contributors. Yes, so then certain things may happen on the one hand, it may simply happen that we cannot calculate the likelihood ratio anymore. If we assume too few contributors, so then we cannot simply fit the data adequately. So the software says cannot calculate or puts out a likelihood ratio of 0 or something like that. Okay, so assume now that we can calculate a likelihood ratio. Then it may happen that low quantity contributors may be excluded. Because they are low quantity contributors, then it usually happens that they are also inclusive when we use the correct number of contributors, but if we use too few contributors, then they will be excluded. What happens for non-contributors, there the situation is not problematic, because if we have fewer possibilities, then the likelihood ratio usually gets more exclusionary. Okay, I have also one picture for that, only for contributors here. This is again Blicker et al. 2017 with Euroformics, and you have here true number of contributors here is 4, and here on the x-axis we have the log likelihood ratio for assuming in the model the same number as the true number of contributors 4, whereas here on the y-axis we assume now too few contributors, so 2 instead of the true number of 4. What we see now is that if we have high likelihood ratio, there it doesn't change much. This is all for contributors, but if we have contributors with low likelihood ratios, so for example minor contributors here in this range here, then from being inconclusive they can get to exclusionary. So here for example you see we have, if assuming the true number of contributors, we have a log likelihood ratio of 0, whereas assuming 2 contributors too few here, then we have a likelihood ratio of about -20. Okay, now I come to the conclusions here. So the first thing I want to stress, also kind of trying to give input in the debate whether using the same or different number of contributors for H1 and H2. So the first point is that using different number of contributors for H1 and H2 is only in very rare circumstances an adequate solution. So it would be a good idea to first concentrate to calculate likelihood ratios for the same number of contributors for H1 and H2. If we then want to have the overall likelihood ratio, then we have a weighted sum of the likelihood ratio for n contributors. So we have to calculate the likelihood ratio for a certain range of n contributors and see whether this changes much or not. So good news is that if we have major contributors, then the number of contributors usually has little effect on the likelihood ratio when we use probabilistic genotype. It might have an effect on minor contributors. As we have seen before, then in this case, decreasing the number of contributors can decrease the likelihood ratio from inconclusive to exclusionary. So we have to take that into account that this might happen. So for non-contributors, so increasing the likelihood ratio can increase the likelihood ratio, so it can change from exclusionary to inconclusive, which I think is not a big issue because as long as it doesn't get incriminating. And my last slide here is just a little bit graphical interpretation about how the likelihood ratio reacts for assuming different number of contributors. We see here on the x-axis we have here the number of contributors. So this is arbitrarily from 2 to 7 here, and here the log likelihood ratio is here on the y-axis. The blue area here is the area where we have inconclusive evidence for the likelihood ratio here. The green area here is where this supports inclusion of the person of interest, whereas here the light red area here, this supports exclusion of the person of interest. Okay, so let's first look at what happens if we have got a major contributor, as we've already seen. So this is a major contributor, so let's assume like kind of first or second major contributor. Then, because it is a major contributor, this will usually get a large likelihood ratio. If we then increase the number of contributors, this likelihood ratio will decrease a little bit, but usually it still stays in the strong support region here. As we say for major contributors, this shouldn't be an issue. but it might be for minor contributors. So in this example here, I've got the fourth major contributor. So if we have in the model only 2 or 3 contributors, then this fourth contributor cannot be included in the model, and therefore we will have an exclusionary likelihood ratio. Only when we have 4 or more contributors in the model, so then the likelihood ratio increases, and usually it increases only to the inconclusive area. Because it's a minor contributor, we usually do not have so much data support for this contributor. And lastly, what happens to non-contributors? To non-contributors, we usually, if we have only few contributors, then we will have an exclusion, and the more contributors are possible, the more increases the likelihood ratio, and therefore it might go from exclusion to inconclusive, which is also kind of logically, because now there are so many possibilities possible. Okay, so that was all about the number of contributors for today. I hope you will get something which to take with you and which to take care about. So I thank you all for listening.
Oh, thank you so much, Anke. That was a fantastic presentation. And I will add as well that this is really instructive, I think, as labs are designing those experiments for validation when they're looking at testing different number of contributors and setting up their propositions. This is a lot of good information to think about as they approach those studies. So thanks so much for participating in our webinar today. Now, at this point, we are going to take a break until 2:15. We're going to be joined next by Zane Kerr, who is he's actually in New Orleans rather than New Zealand at the moment, teaching, and he's stepped away from his class in order to help us out in our webinar today and present his lecture. So that we can check the audio as we go into the break, Zane, I'm going to ask you, if you would please, to go ahead and start sharing your screen, and we'll make sure everything is working. And I will see you all back here at 2:15 from the break. Thank you.
Tamara,
Great,
can you
Zane,
see? Yep, great. Can you hear me?
Yes, we hear you as well. Works good. Thank you so much.
Okay, thanks.
Okay, bye. Okay, welcome back, everyone. We are ready to begin our post-break 2 lectures. I didn't mention earlier that we have Zane Kerr coming up next, and then Bianca Scuta's lecture is recorded from Australia. So we have some of our speakers that are going to be with us till the end of the session. And if you all have any questions, please do send them to us in the chat field. And we'll, if time permitting, we'll try to answer your questions at the end of the session today. So with that, I would like to hand the screen over to Zane to deliver his presentation. Thank you.
Thanks, Tamara. So, as you've heard, my name's Zane Kerr, and I'm a senior scientist within the StarMix team at ESR in Auckland, New Zealand. Today's sessions, we're focusing on the limitations and uncertainties associated with probabilistic genotyping. And while probabilistic genotyping software is undoubtedly a very powerful tool and has significantly enhanced our capabilities as forensic scientists, PG software unfortunately cannot shed light on how or when DNA may have been transferred. From my own experience as a court reporting forensic scientist, I found that the source of the DNA is increasingly not contested, with defence instead proposing innocent means by which the DNA may have been transferred. So in this talk today, I'm going to introduce you to the concept of activity level evaluation, and this enables us to help the court in addressing some of these uncertainties. I don't claim to have all the answers in this area, but hopefully you'll be able to take something away from this talk that may stimulate some further thought and discussion. So I'll just start with a quick recap of the likelihood ratio, or the LR. And the LR is recognised as the most appropriate method to use when evaluating our findings. In fact, all probabilistic genotyping software calculate their match statistics in the form of a likelihood ratio. So I think this really demonstrates its acceptance and support within the forensic community. The LR asks us to consider the probability of the findings given the prosecution scenario. We divide that by the probability of the findings given the defense scenario. In the formula here, you'll also see an additional term which I've indicated with the letter I. And this term represents all of the relevant background information. And you may also see this referred to in the literature as the framework of circumstances. It's often dropped from formula presented in the literature, but you should always keep in mind that it's always there. So in other words, the probabilities that we assign are always conditioned on what we know, what we are told, and what we assume. So in this sense, probabilities are personal. There's no such thing as a true probability. When we take the ratio of these probabilities to find the likelihood ratio, it tells us 2 things. Firstly, the LR indicates which scenario is better supported by the findings. And secondly, it informs us of the relative degree of support that the findings provide for one proposition over the other. The likelihood ratio has a number of significant benefits over other evaluative approaches. First off, it's balanced. The LR forces us to consider at least one alternative proposition when we evaluate our findings. It's also logical. It makes sure that we're addressing questions of the type, what is the probability of the findings given the proposition, rather than considering the probability of the propositions themselves, which is the responsibility of the fact finder. The LR also provides a transparent approach, requiring that we document and disclose the propositions that we've considered, any assumptions that we've made, and any relevant information that we may have used in our evaluation. And finally, the LR is robust. It provides us with a flexible approach that can withstand scientific scrutiny. So the propositions that we consider when we evaluate our findings, they can actually be classified according to the type of issue that they address. This way of thinking about our propositions was first described in the mid-90s, and it's referred to as the hierarchy of propositions. The hierarchy of propositions was actually developed as part of the case assessment and interpretation model that was proposed by the former UK Forensic Science Service. And there are 3 levels within the hierarchy, and they are the offence level, the activity level, and the source level. Level 1 of the hierarchy is what we refer to as the source level. And propositions at this level consider the source of a recovered trace. And if we're considering forensic DNA results, source level propositions, they actually consider the source of a discernible biological fluid or tissue. So an example might be, perhaps there's been a sexual assault and we've recovered from some semen from vaginal swabs taken from the complainant. So the prosecution, they might suggest that the semen originates from the person of interest, while the defence may suggest that it originates from an unknown, unrelated male. When we evaluate source-level propositions, we need to consider the intrinsic properties of the trace. For example, the DNA profile recovered and the results of any presumptive and confirmatory testing that we may have carried out. Moving up, the second level of the hierarchy is referred to as the activity level. Propositions at this level consider activities that may have given rise to the DNA that we've recovered. In addition to considering the intrinsic properties of the trace, we also need to consider its extrinsic properties, such as the amount, location, and distribution of the trace. Operating at the activity level requires us to consider issues pertaining to the transfer and persistence of DNA. If we go back to our sexual assault example, the defence may accept that the semen originates from the person of interest, but maybe they instead propose that the POI and the complainant engaged in heavy petting, which led to the POI ejaculating on the inner thigh of the complainant. In this example, the source of the semen, it's no longer in contention. So those source level propositions, they're no longer relevant. Finally, propositions at the top level of the hierarchy, the offence level, address the ultimate issue being considered by the court. So these propositions typically involve some form of legal element, such as intent or consent, and it's actually therefore really quite rare for forensic scientists to operate within this level of the hierarchy. One example that does spring to mind, though, perhaps might be a medical practitioner commenting on whether some vaginal injuries observed on the complainant of an alleged sexual assault are more likely given rape or consensual intercourse. As the sensitivity of our multiplex kits and instrumentation increased, we eventually reached a point where we could recover DNA profiles from minute traces of DNA where we can't actually determine the biological fluid or tissue that the DNA has actually originated from. This is routinely referred to as touch DNA, although perhaps the term trace DNA is preferable, because low amounts of DNA can also be transferred via mechanisms other than touching. So this actually necessitated an additional level in the hierarchy, one that considers the source of some recovered DNA in the absence of presumptive or confirmatory test results. So because of this, an extra level was added, and this is called the sub-source level, and it sits below the source level in the hierarchy. Now, if we are considering a mixed DNA profile, we could actually go lower still and consider just the source of a particular component of the mixture rather than the sources of the mixture as a whole. And this would represent a sub-source level evaluation. When we move up in the hierarchy, we're actually providing more value to the court, as we're better able to assist the fact finder in considering the issues of interest. However, moving up in the hierarchy requires more scientific expertise and more information in the form of a more detailed framework of circumstances. When evaluating forensic DNA results, we typically operate at the sub-source level. So consider this commonly encountered scenario. Jane, scientist, attends court and presents her sub-source LR for the DNA findings. During cross-examination, the defense attorney states that the source of the DNA is not in contention. They concede that the DNA originates from Mr. POI. However, they propose that it was transferred via some other means, asking Jane if the defendant's DNA could be transferred under the scenario that's been proposed. Jane admits that the DNA could have been transferred by the scenario that's been proposed, at which point the defense attorney asks Jane which transfer scenario is more likely. Jane states that there's many variables affecting the transfer and recovery of trace DNA, and she simply couldn't say which is more likely. What is the jury supposed to make of this information? They need to make a determination on how the DNA was transferred, and they've been given no guidance on this by the expert. Clearly, the expert is in a much better position to consider technical issues such as the transfer and persistence of DNA. In this situation, an evaluation considering activity-level propositions would provide much more assistance to the court in addressing these issues. In fact, I think there's a really real risk here that the jury will mistakenly equate the sub-source LR that has been provided with the activity level issues that have been raised. So careful direction from the expert and from the legal players is needed to ensure that the jury understands that the LR that was presented is no longer relevant. Another comment that I have regarding this scenario is that the expert is being asked to consider these quite complex issues on the fly, and the opinions that she provides have not been peer-reviewed. Ideally, these issues should have been brought to the expert's attention well before attending court.
Hello, everybody. This is Tyler chiming in. It seems we might have lost Zane. So while Tamara is trying to track him down and see what happened, I would like to take this moment to remind everybody that we have recently archived the previous additions to the Probabilistic Genotyping series. So let's see, we're recording today's module, and we've recorded all of the modules leading up to this point, and they're being turned into archival versions over the next couple of weeks. So the first 4 are already for registration and can be viewed whenever you get the opportunity. And then as soon as this module is ready, we're going to send out notifications that will allow you to refer back to this workshop at your leisure. At the end, we're also going to be putting our social media outlet links, as well as the link to our podcast and our website in the chat box. So if you want to take a moment and pop into those and steal some of our information, you'll be good to go.
This example.
Zane, you're back.
Yes, sorry, we're in the middle of presenting.
You're okay. Your audio cut out.
Oh, right, okay.
So,
whereabouts did it cut
I
out?
would go back probably a few slides and pick right back up. Sound good?
All right, I'll just go back. Tell me when to stop.
Okay. You'll have to share your screen again.
Oh, right, okay.
Zane, we lost you as you were describing how the expert is in a better position than a jury to comment on matters pertaining to activity level propositions. You would just begin that discussion.
All right. Okay. I think that was this slide here.
Yes.
Thank you.
Yeah. Okay. All right. Sorry about that. So clearly, in this example here, the expert is in a much better position to consider these complex issues about the transfer and the persistence of DNA. So there's a very real risk here, I think, that if the expert was to just present their subsource likelihood ratio, that the jury may mistakenly think that that likelihood ratio somehow pertains to those activity level issues that have been raised. So in this situation, careful direction from the expert and also from the legal players is required to ensure that the jury understands that this LR that has been presented, this subsource LR, it's no longer relevant. Another comment I have regarding this particular scenario is the expert is being asked to consider these complex issues on the fly, and these examples, these opinions that she's providing have not been peer reviewed. So ideally, these issues should be brought to her attention well before attending court, so that she can consider whether an evaluation at a higher level of the hierarchy is indicated. Doing so would also provide defence with a formal evaluative report that could then be reviewed by their own expert if desired. One final comment is that in this example, the expert is being asked to comment on the probability of particular transfer scenarios rather than the probability of the findings given a proposed activity. So it's ultimately up to the court to consider the probability of the activities that give rise to the DNA findings. So here's another situation. Suppose that our defence expert goes to court and says that she carried out some DNA testing but wasn't able to recover any DNA profile. And the defence may say, well, does that mean that my client didn't touch the item? And our expert responds by saying the absence of evidence is not evidence of absence. So this is a well-known saying, and I'm guilty of using it myself in the past, but is it really fair to the defendant? Suppose that both parties were to put forward some activity level propositions, and our expert here considers the findings.
Yes, and the expert here considers the findings. Eric.
Sorry, is someone speaking? Can you still hear my audio? Okay, so the expert considers the findings in light of those propositions. And so under the prosecution scenario, she might say, well, I actually expect to recover a DNA profile that matches the person of interest. So therefore, the probability under the prosecution scenario of recovering no DNA profile is actually quite low. Under the defense scenario, Jane says that she wouldn't expect to recover a DNA profile. In this instance, the finding that no DNA profile was recovered, it actually supports the defense case. This example also highlights another benefit of activity level propositions, namely that they allow us to evaluate our findings even in situations where we haven't recovered a DNA profile, or where we may have recovered a non-matching DNA profile. So the consideration of an exclusionary profile being recovered, that was actually a central issue that was raised in a South Australian case of R v Drummond, and this ultimately resulted in the conviction being overturned upon appeal. So Duncan Taylor from Forensic Science South Australia has actually published this activity level evaluation regarding this case, which found that the findings did indeed support the defence case when they were evaluated at the activity level. So when should we actually operate at the activity level? Clearly, operating at this level provides much greater assistance to the court, but there is the trade-off that more expertise and information is required.
There is the trade-off.
In what circumstances should we be striving to operate within higher levels of the hierarchy? So if we actually go to the 2015 ENSVI report on evaluative reporting, according to this document, we should be endeavouring to operate at the activity level whenever factors such as transfer and persistence may have a bearing on the scientific findings. The report goes on to state that these factors are especially important in situations where small quantities of DNA have been recovered. The report states that we should only be evaluating source-level propositions in cases where there's no risk that the court will misinterpret the findings in the context of the alleged activities in the case. So in my mind, these ENSVI guidelines really call on us to strive to operate within the activity level of the hierarchy whenever we are evaluating trace DNA results. So how do we actually carry out an activity level evaluation? Unfortunately, there's no one-size-fits-all formula or method, as the process that we employ is largely going to depend on the propositions and on the case circumstances. Evaluations at the activity level require quite a detailed framework of circumstances. So if limited information has been provided, in particular if we've not been provided with propositions, both the prosecution and defence, then we should go out and seek this information. It's also useful to note that task-irrelevant information at the subsource level may actually be relevant when we're carrying out an evaluation at the activity level. For example, eyewitness statements or police interviews detailing the timing of events or the position of individuals at the scene. We typically wouldn't want to have this information or to be exposed to it when we're operating at the subsource level in order to avoid any possible bias. However, this information may prove to be critical if we're carrying out an activity level evaluation. So one approach that's been advocated is for laboratories to appoint someone as an information manager. And this ensures that the scientist is only provided with task-relevant information. This person would need to be trained and experienced in evaluative reporting so that they could properly assess what information is needed while also filtering out that task-irrelevant information. Finally, in cases where the issues reside at the activity level, but where we may lack the necessary information to progress an evaluation, is it acceptable to retreat down to the subsource level? Or does the risk of the court misunderstanding the result outweigh any benefit? Should we instead be reporting that we lack the information required to evaluate the scientific findings in light of the activities that have been put forward? So let's consider an example, and we'll put this into practice. So I've made up some case circumstances, and they are as follows. A woman claims that she's been digitally penetrated by a male individual while she was at a party. The suspect is arrested shortly after the alleged incident. He denies assaulting the complainant, states that the only contact he had with her at the party was a brief hug. A swab of the POI's fingernails is collected and submitted for testing. But based on this information, based on these case circumstances, the issues clearly seem to reside at the activity level within the hierarchy of propositions. What might the propositions be that we're going to consider? Selecting appropriate propositions is one of the most important steps in the evaluation, and this can be really challenging, especially if the suspect has provided a no-comment interview. Propositions that we select should be mutually exclusive, and they should be formulated in the context of the framework of circumstances. Additionally, we should ensure that the alternative proposition is sufficiently detailed rather than just adding the word not into the prosecution scenario. So rather than just saying the suspect did not assault the complainant. So in this instance, it seems reasonable to consider the following propositions. the suspect digitally penetrated the complainant versus he had nothing to do with the assault but had social contact with her at the party. Note also in this example that the defence may actually contest that any assault took place. Similarly, the prosecution may contest that any social contact took place. And these suggestions may have an effect on the evaluation. So it just demonstrates why we really need quite a detailed framework of circumstances to proceed with this activity level evaluation. And finally, we should always be prepared to re-evaluate our findings in light of new information or if alternative propositions are provided. So I'd recommend that you include in your statement something along the lines of what I have on screen here, just to clearly indicate to the fact finder that the evaluation may change if additional information comes to light or if an alternative proposition is put forward. And I'll just point out in this statement that it says that we can undertake that if instructed prior to testimony. So I think the defence really needs to come to the expert well in advance of any court proceedings if they want alternative propositions to be considered. This isn't something that you'll be able to do on the fly, on the stand when giving evidence. So if you go to some of those papers looking at the case assessment and interpretation model that came out of the UK Forensic Science Service, this CAI model calls on the scientists to carry out a pre-assessment of the case before they actually commence their examination. And this involves considering the likely findings under each proposition and then assigning probabilities to these possible outcomes. The list of outcomes that we formulate doesn't need to be exhaustive, but we should try and include all reasonable outcomes. We also should document this formally in the case file, along with the scientists' reasoning pertaining to the probabilities that they have assigned. By doing this before we actually start working on the case, we also help to ensure that we're not being biased by the findings when it comes time to assign our probabilities and evaluate our results. Additionally, carrying out this pre-assessment can actually help us to identify which items or tests that are best able to assist the court in differentiating between those propositions of interest. So this ensures that we're not wasting time and resources examining items that don't actually assist us in assessing those propositions. So what data should we refer to when we assign these probabilities? Ideally, we would carry out case-tailored studies, reenactments that try to model the specifics of the case as closely as possible. However, due to limited resources within most case-working forensic laboratories, this typically won't be possible. So in this instance, what we can do, we can instead refer to studies and surveys that approximate the case at hand in some regard. It's preferable that these studies have been published in the peer-reviewed literature, but if not, we can use internal studies that we may have carried out within our own laboratories, provided that they are subsequently disclosed for review and examination. As a last resort, we could also fall back on our training, education, and experience and use this to assign what we might term as subjective probabilities. It's important to note, however, that we need to be prepared to justify the probabilities that we assign and provide documentation that outlines the reasoning that led to us assigning those probabilities. It's simply not sufficient to say that I've been an expert for X years and based on my extensive experience, these are the values that I've assigned. Now, the thought of having to go out and assign these subjective probabilities may make us quite uncomfortable, especially if limited data exists. We may wish to retreat into the comfort zone of the subsource level. But I think the following quote by Ian Evatt really puts things into perspective. And Ian Evatt states that there's nothing unscientific about subjective judgment provided it is exercised with discipline within a logical framework. It's also worth keeping in mind that other forensic disciplines, for example, glass and fibers, they've been assigning these subjective probabilities for many years. There's a number of things to keep in mind when you go out and review the available literature for relevant studies. Firstly, we need to consider that the methods used may differ to the ones that we use in our own laboratory. So there could be differences in the recovery techniques, DNA extraction chemistry, quantification method, the multiplex kit that's being used, PCR conditions, and the CE instrumentation. And these can all have an effect on the results. So, for example, you may find a paper that addresses the exact scenario that you're interested in. However, the testing has been performed in that study using a less sensitive DNA extraction technique than what you use in your laboratory. So in this instance, you may actually need to go out and find some additional studies that compare the sensitivities of the two extraction methods and then adjust your probabilities accordingly. Another difficulty is that there's no consistency in how results are reported or classified. So what you'll find is that some studies will group results based on qualitative descriptions of the DNA profile, while others may make use of quantification results or allele counts. This lack of consistency can make it really difficult to compare results between different studies. So you may actually need to extrapolate the data you need using what information has been provided. So an example of this, if quantification results and mixture proportions have been provided, you can actually use this information to calculate the approximate amount of DNA in the sample from each individual contributor. Failing this, you may actually need to chase up the authors of the paper to see if they're able to provide you with the information that you need. Let's get back to our little case study. So first we need to consider the findings that are likely under the prosecution scenario. We can use the results of relevant scientific studies to guide us in this task. So in this example, we need to find data on the recovery of non-self DNA on fingernails following digital penetration. It just so happens that there are papers looking at this out there in the literature that we can turn to. So I've used this one here by Flanagan and McAllister, and based on this study, I would say that I'm expecting to recover DNA from the victim on the POI's fingernails. So I've assigned these following probabilities. I've assigned a probability of 94% to the recovery of the complainant's DNA on those fingernail swabs, and only a chance of 6% of not actually recovering her DNA. Under the defense scenario, what we need to do is consider the transfer of an individual's DNA to another person's fingernails following routine social contact. So again, a review of the literature reveals several studies that look at the prevalence of foreign DNA under fingernails. However, one thing I found with these studies is that they didn't investigate the source of this DNA. And there's actually been other studies that did look at the source and found that where there is foreign DNA under someone's fingernails, it most likely originates from the partner of that individual. So therefore, the foreign DNA that was observed in these other studies may actually be from intimate contact between cohabiting partners rather than from routine social contact. So in the end, I decided to use this 2013 paper by Maria Gore and Roland van Oorschot from the Victorian Forensic Lab in Australia, as they differentiated between DNA transferred to hands following social contact with the other study participants and foreign DNA that didn't originate from any of the participants involved in the study. So studies examining the amount of DNA transferred to hands following handshaking experiments could also be of use in this situation. But based on this study, I've assigned the following probabilities. So I've assigned a probability of 0.2 to recovering the complainant's DNA on the POI's hands or on his fingernails following just innocent social contact, and a probability of 80% to recovering none of the complainant's DNA on the suspect's fingernails. There are some other considerations. First, we've only considered the presence or absence of DNA from the complainant, and this is because that paper by Gore and Van Oorschot only reported on the proportion of hand swabs that had DNA from another participant. There were no details provided regarding whether the profiles were single source or mixed, full or partial, etc. Therefore, we've not considered the amount of DNA from the victim or the profile quality. Ideally, we could use more precise categories to account for this, and doing so may actually provide us with a more discriminating likelihood ratio. Another consideration is the fact that this study by Gore and Van Oorschot examined swabs from hands, whereas in this present case, we're actually dealing with a swab from the fingernails of the suspect. Could there be a difference in the rates of DNA transfer, persistence, and recovery between these two areas of the hand following social contact? These limitations don't preclude us from carrying out an activity level evaluation, but we should make a note of them in our case file when we assign our probabilities. We could also examine the effect on the likelihood ratio if we were to assign different probabilities to these transfer events. This is referred to as carrying out a sensitivity analysis, and I'll demonstrate this later on in the talk. Depending on the propositions and the findings, we may also need to consider the prevalence of background DNA. In the present example, however, it can actually be demonstrated that the terms for background DNA will actually cancel out when we derive our likelihood ratio formula. But if we did need to consider background, studies such as these ones, looking at the prevalence of foreign DNA under fingernails within the general population, might be of assistance. So when we derive our likelihood ratio in this case, we can actually show that it's approximately equal to this term here, TV divided by TS plus TV0. TV is the probability of DNA from the complainant transferring, persisting, and being recovered from the suspect's fingernails following digital penetration. TV0 is the probability that no such DNA would transfer, persist, or be recovered from fingernails following digital penetration. And TS, that's the probability that DNA from the complainant would transfer, persist, be recovered from the suspect's fingernails following routine social contact. So using those probabilities that we assigned during case pre-assessment, we can now evaluate the likelihood ratio. So we can substitute in terms for those transfer probabilities. And we arrive at a likelihood ratio approximately 4.76. So we might report this by saying that it's approximately 4 times more likely to obtain these results if the suspect digitally penetrated the complainant rather than if he had nothing to do with the incident. We could also report the strength of the findings using a verbal qualifier. For example, we could say that these findings provide limited or slight support in favour of the prosecution scenario versus the defence scenario. As I mentioned earlier, if we have limited data and we're unable to confidently assign these probabilities, we can carry out what is referred to as a sensitivity analysis. So note that this is different to the sensitivity and specificity studies that you may have done in your lab if you have validated PG software. Now, a sensitivity analysis in this context involves changing the probability assigned for a variable across a range of sensible values and then observing the effect that this has on the likelihood ratio. More complex examples of these sensitivity analyses can actually adjust the probabilities assigned to multiple variables simultaneously. So let's suppose that in our case, a defense expert has been brought on and they've actually brought to our attention an alternative study looking at DNA transfer during social contact. And that other study actually found larger rates of DNA transfer, and they've said to us that they feel that we should be assigning a larger probability to that term TS. Remember, that's the probability that the complainant's DNA will transfer, persist, and be recovered from the POI's fingernails following innocent social contact. So what would happen if we instead assign a value of 0.4 to that term? What effect would this have on our likelihood ratio? The net result is that our likelihood ratio is approximately halved. Note, however, that the findings still provide support for the prosecution proposition, and the level of support is still within the same order of magnitude. So in this example, doubling the probability of recovering the complainant's DNA following social contact has not actually resulted in a substantial change to the likelihood ratio. So the evaluation of our findings in light of activity level propositions can become really quite complex. And one approach that's really gaining a lot of traction is to use what's called a Bayesian network, and these are also referred to as Bayes nets. So these are a graphical representation of the evaluation, and they quite clearly show the variables and the dependencies that we have considered in our interpretation. So they're quite transparent. They enable other experts to see exactly what we've done in our interpretation. It's also worth pointing out that Bayes nets are not a new thing. They've been used for many years in other fields, such as in medical diagnostics, where decisions must be made in the face of uncertainty. Bayesian networks consist of nodes that represent the variables we're considering and arcs that connect these nodes. We use these arcs to show dependencies between the variables that are being examined. Sitting behind each node is a probability table. These tables indicate the states that the node can take and the probabilities that have been assigned. Where a node has one or more incoming arcs, the probabilities assigned will be conditional on the parent nodes. If you're able to first derive your likelihood ratio formula, this can then actually be used to assist you with the construction of a Bayesian network, as the LR formula will indicate the different variables that must be considered along with their associated dependencies. However, in practice, this often works in reverse. The problems are so complex that we simply cannot derive the likelihood ratio formula by hand, so instead we use a Bayesian network to evaluate the likelihood ratio. So I'm going to provide a really basic example just to show you what a Bayesian network looks like and how they're constructed. So I'm going to use this disease testing scenario. This is commonly used to teach Bayes' theorem, so you might have even come across this example yourself in the past. So let's imagine that you're a physician and a patient that you're treating has tested positive for a disease. You know that the prevalence of this particular disease in the general population is 1 in a million. The false positive rate for the test that we've used is 5%, and the false negative rate is 1%. So what's the probability that the patient is actually diseased, given that we've seen a positive test result? So let's construct a Bayesian network to help us assign a probability to the patient being diseased given the test result. So first, I'm going to add a node that represents whether or not the patient is ill. I've called this node diseased. Sitting behind this node is a probability table where we specify the states that this node can take. But obviously there's going to be 2 states here. Either the patient is diseased or they're healthy. And you can see that I've assigned a probability of 1 in a million to the patient being diseased, and a probability of 1 minus 1 in a million to the patient being healthy. This is just using our prior beliefs based on the prevalence of the disease within our general population. I'm then going to make another node, and this represents our test result. And then there's going to be two states again for this disease, test result positive and test result negative. But the outcome of our test result is going to depend on whether the patient is diseased. So I'm going to add a node an arc connecting those two nodes. Sitting behind the test result, again, is a probability table, and these are going to be conditional probabilities. So they are going to depend on whether or not the patient is truly diseased or truly healthy. So here you can see the false negative rate of the test. Here's the false positive rate of the test. Now that we've constructed our Bayesian network, we then need to tell it what our test result was. And this is referred to as instantiating the node. So I'm going to instantiate the test result node, the positive, tell our Bayesian network that we have observed a positive test result. So now that we've instantiated that test result node, we can then read the posterior probability of the patient being diseased from the diseased node. So in this example, the probability that the patient is diseased, given that we have seen a positive test result, is actually less than 0.2%. So this may seem counterintuitive, but it's simply due to the fact that the disease has a very low prevalence. Nevertheless, the positive test result has increased our belief that the patient is diseased relative to our prior beliefs before we saw that test result. So we can actually use Bayes' theorem just to confirm that the result that is being produced by our Bayesian network is correct. And here, using Bayes' theorem, you can see that I arrive at the same posterior probability for the patient being diseased, given that we've observed a positive test result. Now, in this example, we have calculated the posterior probability, but as discussed earlier, this is really the province of the court to consider. So how can we use our Bayesian network to evaluate the likelihood ratio? If we set even prior probabilities in the disease node, so here you can see I've set probabilities of 50% and 50%, then we can actually calculate the LR quite easily simply by taking the ratio of the probabilities that are displayed in the diseased node when we instantiate the Bayes net. So here I have instantiated the test node as before, and I've calculated the LR simply by taking the ratio of those probabilities that are displayed next to the disease node. So you can see that our likelihood ratio is approximately 19.8. And again, we can just confirm that result by hand, and we arrive at the same likelihood ratio. So this example has been really basic, but hopefully you can appreciate that for more complex situations that have many variables, it may be next to impossible to assign a likelihood ratio by hand. So it's these situations where Bayesian networks really shine in helping us evaluate our results. Many examples have been published demonstrating the utility of Bayes nets to evaluate forensic biology results. And here are several references that you might like to refer to for some further information. The 2018 paper by Taylor et al., it's particularly helpful. It presents a template that can actually be followed to construct a Bayes net, considering activity level propositions for forensic biology cases. So I'll wrap up now just by touching on some future directions and developments. Firstly, the development of guidelines and a standard approach regarding how data on transfer, persistence, and prevalence are reported and presented within the scientific literature would facilitate comparison of results between studies and evaluation of the suitableness of the data for the case at hand. The development of a searchable, centralized repository of transfer, persistence, and prevalence studies would also be welcome. The potential format and content of such a repository was discussed extensively by Cockshorn et al., and recently Gosch and Courts have taken the first steps to addressing this need with DNA Track, and this is a Microsoft Access database that contains information from a large number of studies. This database could further be expanded and developed in ways suggested by Cockshorn et al., for example, by allowing users to upload their own Bayesian networks that they've constructed when evaluating case results, or perhaps by adding a forum where users can seek guidance from other forensic practitioners. The evaluation of forensic biology results given activity level propositions will likely be quite a new concept for forensic scientists, along with our stakeholders such as police and legal practitioners. Training is going to be needed in order to successfully implement evaluative reporting within laboratories and have it successfully introduced at court. To this end, several formal courses are offered online by the University of Lausanne in Switzerland, and the university has also developed a free online course that's housed on the Coursera platform, which introduces many of the key concepts and principles developed in their other courses. Activity level evaluation is really starting to gain traction, and currently there's a really big push in Australasia and in Europe for labs to start doing this. Perhaps the first step, if you're keen to implement activity level reporting in your lab, is to reach out to other labs that are already doing this and to seek their guidance. If you are not already reporting likelihood ratios, maybe start by implementing evaluative reporting at the subsource level, just so that your staff and the legal community can get some exposure to likelihood ratios and get some familiarity with that approach. There's also some guidance and recommendations available from professional bodies, such as the Australian New Zealand Policing Advisory Agency, National Institute of Forensic Science, or ANSPA-NIFS, and also the European Network of Forensic Science Institutes, which I referred to earlier on in this talk. So the NSFI guidelines, they're particularly helpful, and they include a number of examples of activity level evaluation across several different forensic disciplines. So hopefully I've demonstrated to you today that rising within the hierarchy of propositions allows us to better assist the court in their deliberations. There is a very real risk that we may mislead the court if we operate within lower levels of the hierarchy, such as the subsource level, when the issues before the court actually involve how or when the DNA was transferred. Ultimately, we as experts are in the best position to consider how these issues may impact our findings. Providing an activity level evaluation does require us to assign probabilities. This can be difficult and there are challenges involved. However, we can use our professional expertise and judgment to assign robust probabilities that can withstand scientific scrutiny. And finally, Bayesian networks provide a powerful solution, especially when dealing with complex case scenarios that may have many variables that need to be considered. They're widely recognized as the best solution to evaluate our findings, given activity level propositions, and articles have been published with guidance on how to construct Bayes nets for our forensic biology results. Thanks for listening. I'll stick around now for a moment if you've got any questions, but if not, please feel free to contact me via email if you have any further questions. Thank you.
That was fantastic, Zane. Thank you so much for assembling all of that information for us and presenting today. We did have one question, and it's a little bit off topic, and I'm going to share my screen so you have the ability to see this question.
Okay.
I'll find it here. Okay, so here under question 7, it's a question in general about how can LRs be amended if the person of interest is found via a database search such as a CODIS search? So I guess that question is in the context of should it be amended, or is that getting at a different question for the court or a different set of propositions?
Sure. Well, I guess I can offer my 2 cents. So I think back in the NRC 2 report, a recommendation was made to adjust our match statistics if the match has been identified through a search of a database. And there was a lot of discussion around that period in time from many different parties as to whether adjusting our match statistics is appropriate. Personally, I don't think that they should be adjusted. If anything, the results, the likelihood ratio would actually increase. It would actually provide further support against the person of interest if we were to make such an adjustment. And this is because our forensic DNA databases, they do contain the profiles from, a large number of individuals, I guess, in what you would call the active criminal population. So if we search our DNA profile against a database and we find one match to one person of interest, really what we should be considering is that we have effectively excluded all of those other individuals within the database, which actually would, if we were to take account of it, would actually increase our likelihood ratio a little bit. So back in the day with NRC2, I believe the proposal was to adjust the match statistic to lower it so that it's counting for the size of the database. But logically, I think when you think this through, it should actually increase the strength of the result. I mean, you could take this to the extreme example. If we had every single person within our population in a database, we have searched our DNA profile against that database and found one match, then the DNA could only have come from that individual. We have actually excluded every other person in that population. So it doesn't really play into, I guess, the activity level evaluations, as I discussed, where the source of the DNA is not actually in contention in those situations. But certainly there have been a rigorous debate as to how we should factor in the search of a database into our match statistics. Generally, I think if we don't account for it, we are being conservative, because logically, if we did account for it, it would actually increase the strength of the findings against the person of interest.
Tamira, can I also say something about that?
Sure.
Yes, please.
Yes, so I also like to support what Zane says. I think there has been a lot of debate about that. I think most people now agree that the likelihood ratio will only increase a little bit if you take that into account. But you have to take it into account when you look at the prior distribution. So if you have a suspect identified by other strong evidence and then have a match, then the prior, of course, is much higher, even if you have the same likelihood ratio. Whereas if you have found the person only by the database search, the prior will be much lower. So usually you wouldn't adjust the likelihood ratio. That's conservative, but you have to take care of the prior if you have any other evidence or so.
Yes, sorry, I should have mentioned that. Yes, so I mean, we as forensic scientists, the priors and the posteriors, they're not really our responsibility, but hopefully when those results are presented to the court, if that's the only result that there is, if there's no other information or findings linking that defendant to the crime, then hopefully the jury would actually assign priors that perhaps favour the defence scenario. So as Amki pointed out, the likelihood ratio doesn't change, but the priors change, and that will actually lead to a difference in the posterior odds that the court would assign.
Great. Thank you both for that discussion. And while I have you here on the screen, there was one question, and I think it's very straightforward from last week that we weren't able to get to. The reports that you're familiar with, it's the one directly above. The reports that you're familiar with, are the propositions actually spelled out in the report?
Yes, so you can infer, certainly in StarMix, you can infer what the propositions are, looking at what individuals were included under the prosecution and defence scenarios, and also the number of contributors that have been assumed. I do have some experience with true allele as well, and that also similarly points out the propositions that have been considered. So they are listed in the report.
Okay, very good. Yep. All right. Well, thank you, Zane, so much for your presentation today. It was very informative and very helpful.
Thanks, Tamara.
With that, great. So with that, I would pass it back to the folks at RTI. There's so many people in the background here that are helping to put on the webinar, and they, at this point, are going to be running the video from Bianca Scuda, and I hope you all can stick around with us because I think she's going to be talking about some of the research that's related to this important topic that Zane was discussing for us today. So we're ready to roll with the next presentation. Thanks.
And welcome to all those who are tuning in from all parts of the globe. Today I'm going to be talking about DNA transfer, persistence, prevalence and recovery, which I'm going to refer to as DNA TPPR, because let's face it, repeating DNA transfer, persistence, prevalence and recovery over and over again is just not fun. And so we're talking about that in the context of the relevance of a DNA profile. So I really just want to focus on what DNA TPPR is, and the body of work that has been and is currently being performed on the factors that are associated with DNA TPPR. Now, much of the content that I'm going to present today can be found within a review paper that was actually published in FSI Gen earlier this year. So I just wanted to take the time to acknowledge the other co-authors on this paper, so Roland, Georgina, Bus, and Maria. And lastly, although this presentation is pre-recorded, I just wanted to strongly urge you all to ask questions throughout, and hopefully I can provide a response in another module. So why is it important to understand DNA TPPR, and why am I going to take up 45 minutes of your time to talk about it? Well, it's something that's been mentioned quite a lot over this webinar series, and that's the increased sensitivity of profiling systems over the past decade. And so this has led us to retrieve profiles from decreasing quantities of DNA. We also have an increased reliance on biological samples within criminal investigations, especially from touched objects. And these two factors has led to an increased number of profiles from multiple individuals. And so more and more, there's this requirement to understand how the DNA within a trace sample got to where it was collected from, and not just who might contribute. Often in court, the issue is not the origin of the DNA profile, but the activity that resulted in the crime stain. As discussed by Dr. Peter Gill in Module 1, this requires one to evaluate the DNA results given activity level propositions. And just like considering the rarity of a DNA profile within the population of interest, as one would do when considering source-level propositions or sub-source-level propositions. Factors associated with DNA TPPR need to be considered. I don't want to go into the evaluation side of things any further, as there is a presentation dedicated to the hierarchy of propositions and activity level reporting in this session. Instead, I just want to highlight the knowledge that we currently have on DNA TPPR, and I'll leave it up to the others in the session to discuss how to use the knowledge. DNA TPPR, is relevant to all biological materials. However, much of the recent literature focuses on the transfer of DNA traces through contact with the skin surface. And the main reason for this is that these types of samples are increasingly being targeted in criminal investigations. So the need to understand factors associated with contact traces is becoming more widely recognised. So a lot of what I'm going to talk about today relates specifically to contact traces. And so the variables that I've presented here are by no means not exhaustive. There are a range of core variables that are currently known to impact DNA TPPR, and I'm going to touch on each of these and highlight what's been done. But of course, there are many others that potentially have not yet been discovered or are known. Also, these variables are not necessarily discrete. For example, DNA recovery and the ability to collect a DNA sample is influenced by substrate. And yeah, so there's quite a lot to get through in 45 minutes. So I'm going to apologise in advance if I skim over some of these. But I'd again like to refer you back to the transfer review paper if you're looking for some more information on these variables. So before I start talking about variables, I just wanted to touch on terminology. Because we're talking about activities, it's important to use appropriate terminology that reflects the situation. And so some of the terminology that we currently use implies a specific association or activity that might not necessarily be true. For example, trace DNA has multiple definitions. It can refer to the quantity of DNA in a sample, whether it's attributable to a bodily fluid, or perhaps the uncertainty of its association to a crime event. Touch DNA implies something's been contacted or touched. Skin DNA implies the source of DNA from skin. Wearer DNA implies something's been worn. And again, like trace DNA, background DNA has multiple definitions. And so in a perfect world, we would all come to a consensus on the terminology that's being used. But we're not there yet. So it's important really just to avoid using potentially misleading terminology or to use neutral terminology when the source or action is unknown. But at a minimum, provide definitions or indicate the limitation of the terminology being used. Sorry, just some technical issues there. So that then provides a perfect segue into DNA transfer and the meaning of associated terms. If there's one thing that research on DNA transfer has shown us, sorry, I've gone too far. DNA transfer has shown us it's that there are various routes that DNA can be transferred. And of course, there are different terms that are used to describe the modes of transfer, such as direct and indirect transfer, which are probably the most well known. Terms direct and primary transfer are used interchangeably or tend to be used interchangeably, such as the same goes with indirect and secondary transfer. However, with the term secondary transfer, it tends to suggest that there's only two steps of transfer in the pathway. However, the source of the DNA might have been transferred multiple times. So again, thinking about terminology, it's important that we're clear on what's meant by secondary transfer within the context of the scenario. So following a transfer event, it's important to consider that any additional contacts with that surface will diminish the amount of DNA on that surface. And the level of reduction will be dependent on a number of factors, including the substrates involved and the manner of contact. So any object or surface that's involved in a multi-step transfer pathway may come into contact with other surfaces and items and could potentially result in multiple divergent transfer pathways. And again, DNA will typically diminish as contacts increase. DNA can also be temporarily deposited on a surface during a transfer pathway and then recollected again prior to contact with the surface of interest. And we've coined this DNA parking. So specifically in reference to hands, which we know are vectors for the collection of other DNA within the environment, one contact event can also simultaneously include both direct and indirect transfer events. So for example, you've got contact between a hand and a surface, and this may result in the transfer of DNA from the person making contact, as well as any other DNA that might be on the hand from previous contact. In addition, transfer might be bidirectional. So when the hand's coming into contact with the surface, where DNA is already residing, the hand can transfer DNA to the surface, and then the surface can transfer DNA back to the hand. And so just bringing you back to the diagram that I showed earlier, the complexity of DNA transfer is that it can take on any one of those routes, or take any one of those routes, before, during, or after a crime event. And so the expert's role is really crucial here to translate the knowledge that they have on DNA TPPR issues to the court, and that's generally gained from research on DNA TPPR. So earlier work on DNA transfer identified a number of core variables that are currently known to have an impact. These studies found that the composition and porosity of the substrate on which DNA resides and the nature of the substrates that they come into contact with will impact how much DNA is transferred between the surfaces, as will the manner of contact between two surfaces, so whether it's a simple touch or there's some movement between the surfaces, such as rubbing. For DNA traces that are deposited through touch, the freshness of a deposit does not generally impact DNA transfer, as it would with other biological fluids, such as blood and saliva. However, this does appear to be dependent on contact manner and substrate, and so, as I said earlier, there's some interaction between these variables. So since this earlier work, there have been a number of other studies that have highlighted the impact of these variables on DNA transfer. Studies looking at the ability to recover DNA transferred by the hands to different substrates have consistently found that greater quantities of DNA are retrieved from wood and fabric compared to glass, metal, and plastic. This study looked at the transfer of wet and dry blood between substrates. They found that because blood tends to behave differently when deposited and also dried on different substrates, the different makeup of the surfaces not only influenced the transfer of the biological material, but also the collection and extraction of DNA. So what these studies do is just really highlight the importance of considering substrate impacts on DNA transfer and recovery. Another study looked at the transfer of blood and the impact of drying time under different conditions. They found that blood dried relatively quickly, so generally 30 minutes to an hour, but that was dependent on temperature. So blood tends to dry quicker in warmer temperatures compared to cooler temperatures. They also found that transfer rates were similar between the 4 conditions tested during the first 5 minutes, and again for any time greater than 60 minutes. So you can see down the bottom there where the graph plateaus. And what this shows us is that it's important to consider the timing of a transfer event relative to when the biological sample in question was initially deposited. The way in which an object or surface is contacted also impacts DNA transfer. So studies have shown that a substantial amount of DNA is transferred during the initial contact with a surface or item. This actually relates to singular contact, so not repetitive contact, which would result in different transfer rates. And as I mentioned earlier, initial studies showed that more DNA is retrieved following friction and pressure contact compared to passive contact. And this was demonstrated in a simulated break-in where different intensities of handling tools actually impacted the types of profiles that were retrieved. So specifically relating to contact traces, the area of a hand making contact will also impact DNA transfer, with different parts of the hand actually collecting and transferring DNA at different rates. So when contacting a flat surface that contained DNA, this study showed that the fingertips appear to collect and transfer more of the DNA than other parts of the hand. And interestingly, the quantity of DNA is not proportional to the size of the surface area contacted. So the smaller surface of the fingertip could actually transfer more DNA than the larger surface area of the palm. Also relating to contact traces, sheddar status is a term that's being increasingly used to describe an individual's ability to transfer their own DNA to a surface upon contact. Initial studies on DNA transfer observed differences among individuals in the quantities of DNA that they deposited. They suggested that some individuals are good shedders and some are poor. Since then, Gore et al. Performed an in-depth study, and they found that that is correct, that some individuals do consistently deposit more or less of their own DNA than others. And this actually remained consistent over time. So it's not influenced by the time of day that the deposit was made, hand size, whether it was the left or right hand, what the individual's hand dominants were, and those types of things. Sheddar status has also been demonstrated using fluorescent staining of cellular material deposited through touch. So based on the quantity of cellular material deposited, individuals were then categorized as heavy, intermediate, and light shedders, and this was regardless of the hand used, so the right or left hand. The implications of sheddar status in simulated scenarios has also been studied. So in this particular study, following an attack scenario, they found that there were differences amongst individuals in their tendency to transfer their DNA onto T-shirts. And this was true for both the wearer and the simulated attacker. And they concluded that there was a higher probability of detecting DNA transferred from a high sheddar than from a low sheddar. In a DNA transfer simulation via handshake, followed by immediate contact with 5 glass plates, the relative shedding ability of the pair determined whether the depositor and the opposing handshaker were detected in the profiles obtained. So the handprint depositor was actually excluded from several of their own handprints, and the opposing handshaker was detected. And so it was determined that if the opposing handshaker was a good shedder, they could actually swamp DNA from the depositor if they were a poor shedder. So while there's evidence that some people shed more DNA than others, the factors that influence this are unclear. And there are various sources of DNA on the hands that might contribute to one's sheddar status. Regarding the self portion, it appears that majority of the cells, or the DNA, is cell-free rather than contained within cells. And there's also suggestions that a large amount of what we see on the hands is actually derived from other areas of the skin and the body, as well as other bodily fluids. And then, of course, there's the non-self portion, which is collected through contacts with the environment, and that can be derived from just about anything. Studies have also found that even different areas of the hand can have different transfer rates due to the production of sweat and sebum. Factors such as skin conditions, age, sex, as well as behavioural traits can also have an impact on one's ability to deposit DNA. So given all of these factors can contribute to a person's ability to deposit DNA, what's not clear is how to categorise an individual into a class or to allocate them a score. I suppose in a practical sense, how to determine the sheddar status of an individual or a person of interest at some point after the time or after the event of interest. Some other issues with sheddar status relate to the terminology. So how appropriate are the terms sheddar status, and good and poor sheddar? These tend to suggest that it's possible to categorise an individual based on how much DNA they deposit, but we do not currently have a standardised scale. These terms also might imply that DNA is skin-derived because it indicates an action, so the skin being shed. But what about cell-free DNA and material from other sources? Also, the terms imply that, or have a perceived to imply that all the DNA deposited is self-DNA from the actual donor. But again, what about self-DNA that's acquired on the hands or on the skin? So just to recap, the composition and porosity of the substrate on which DNA resides and the nature of the substrates that they come into contact with will impact how much DNA is transferred between surfaces, as will the manner of contact between two surfaces. The freshness of a deposit of deposited biological fluid, so such as blood and saliva, will impact transfer rates, but this is not necessarily so for contact traces. So within the context of a case, it's important to have knowledge of the history of the item of interest, as well as any relevant contacts with the item and surfaces. And it's really important to be aware of common ways of handling or using items that may result in differences in transfer rates, as well as being aware of using appropriate terminology. So studies have found that there is consistency in the amount of DNA that an individual can deposit. There's also an association with the amount of DNA collected from items associated with the individual or with an individual, as well as their relative contribution within the profiles obtained. And this is important in indirect transfer events as it does impact detectability. So while research suggests that genostatus is real and we do need to take it into consideration, there are issues with its application in casework, so such as how do we determine someone's genostatus post-offence, and again, we don't have a standardised scale or a consensus on terminology that's being used. So moving on to DNA persistence. When considering the likelihood of transfer, we tend to focus on the variables impacting the original deposition and the variables at the time of collection, so from the surface of interest. But it's actually really important to consider the activities as well as the variables that impact the persistence of DNA in the period of time between the two events of interest. So when there's no further use of an item or surface, persistence is impacted by time and environmental factors, but there might also be continued use of the item or surface by the same person, by another person, or by multiple people. So this study here on the persistence of DNA in blood and contact traces in different environmental conditions is hot off the press. It only came online a couple of weeks ago, and I was actually really glad to find this, as there are very few in-depth studies that have looked at persistence of DNA over time and under different conditions. And they found that under indoor conditions, that DNA within blood persisted for over a year, while for touched objects, the DNA persisted for up to 8 weeks before partial profiles were observed. And articles left outdoors, so this is true for both the blood and for the contact traces, they showed highly variable persistence rates, and that was subject to the weather. So this study was performed within a tropical climate and some rain was experienced. An earlier study that looked at the persistence of DNA within buffy coat deposited on surfaces left outside and also stored inside reported similar findings to the previous study, though they had a more limited time frame of 6 weeks. And studies have also looked at the persistence of indirectly transferred DNA on knife handles that were left for up to 1 week within a lab environment. They found that the detectability of the indirectly transferred DNA actually decreased over time. And so what these studies do, looking at the persistence of DNA over time, they demonstrate that it's really important to collect samples as soon as possible after an offence. So when considering DNA transfer, there's often a focus on the initial activities that lead to the DNA question being picked up from a particular item or surface, and then on the activities that surround its deposition at the location where it's sampled. But there's often, again, this time lapse in between these actions, and any contact can influence the gain or loss of DNA. And so these studies here analysed several videos of individuals performing various general activities, as well as during armed robberies and unarmed robberies. They found that individuals actually come into contact with several items over a relatively short period of time. And of course, this is going to impact on the transfer of self and non-self DNA. So looking again at the transfer simulation via handshake that I showed earlier, followed by immediate contact with 5 glass plates, you can see here in the graph that deposition of self DNA from the depositor and non-self DNA from the opposing handshake actually decreases as contacts increase. You can also see a lot of variation in the detectability of self and non-self DNA, but this is expected, as I said earlier, given the variation in participants' ability to deposit their own DNA and to transfer. So looking again at the same study, but following a 15-minute delay between the handshake and contact with the glass plates, where participants actually went back to their normal routine and their normal activities, you can see that deposition of self DNA actually follows the same trend. It still decreases as contacts increase, but there's much less non-self DNA from the opposing handshaker. Excuse me. Interestingly, the persistence of non-self DNA from the opposing handshaker was actually dependent on the activities performed and the objects contacted between that 15-minute delay. So multiple contacts with the same items actually increased the likelihood that opposing DNA from the opposing handshaker would be retained and then detected in the deposits. So following use of an item by another individual, we see a progressive increase of the second user relative to the original user over time. In this particular study, they found that the second user was the major contributor in 55% of samples after 2 hours of use, although DNA from the original user persisted long after use by the second person. And again, interestingly, DNA from unknown individuals was found in 71% of samples, though they were mainly detected as the minor contributor in those profiles. So other studies have looked at persistence of an original user after use by another, and they found similar findings to the previous study that I mentioned, especially in respect to the detectability of the original user as well as the second user and the finding of foreign DNA. Other studies have looked at the persistence of DNA after washing, as well as the persistence of semen in the vaginal cavity, but in the interest of time, I won't go through these, but again, I'd direct you to the transfer review paper if you're interested in this. So just to recap, it's important to have an appreciation of the activities that may have occurred during the time between key activities of focus, and the potential impact of these activities on what is deposited at the final collection site is considered. This is especially important when evaluating the weight of evidence when propositions are at the activity level. So when a sample is collected from a scene, there may be multiple known and unknown sources that contribute to the profile obtained, and these sources might have contributed either prior to the offence, so DNA residing on the item or surface from previous uses, during offence, so directly or indirectly transferred DNA during the commission of a crime, following the offence, through further use of the object or space by the same person, different individuals or multiple individuals, or again, following the offence through contamination by investigators or lab personnel. And there are different terms that are used to describe the contributing sources that might be found. So DNA prevalence refers to the presence of cellular material or DNA of the person of interest on a surface or in the environment, while background DNA relates to the presence of cellular material or DNA from unknown or known but irrelevant individuals within the context of a case. So focusing specifically on background DNA on the hands, studies have shown that a large portion of DNA that actually resides on the hands is non-self, though generally it's observed as a minor component in DNA profiles obtained. When the hands come into contact with the surface, this non-self component is generally deposited along with self DNA, and again, it's usually detected as the minor. But only in a small number of samples was the background DNA actually the major contributor. Background DNA has also been observed on other areas of the body, such as the face, neck, wrist, arm, and fingernails. As with the hands, generally the non-self component was observed as the minor contributor within the profiles, with the exception of fingernail samples where the background DNA or the non-self has actually been detected as a major contributor. The prevalence of human cellular material on public and private objects has been investigated, and this study here found that public objects, which I suppose are generally shared items between multiple people, they yielded fewer profiles with a major contributor, so there was no distinction between the components within the profile, while for private objects, 88% showed a clear major contributor, and this was always this always corresponded to the owner of the item. So while both public and personal items often have some background DNA on them, shared items often provide mixtures comprised of multiple individuals. There have also been a number of studies that have looked at the prevalence of DNA on different areas of clothing, and background DNA is often observed in the profiles obtained. So these studies here collected a limited number of reference profiles, but they actually found that family members who lived with the wearer of the clothing item often contributed to the background DNA that's observed on clothing. So unless new or cleaned, most surfaces and items will have some DNA on them from previous use, and the amount of DNA on the items will depend on the level of use and who uses them. But I suppose the most important point is that background DNA has the potential to interfere with profile interpretation, and so having an awareness of the general levels of background DNA, just quantity and the origin, is useful in deciphering what might be found on items and surfaces in various situations and environments. Also, when targeting an area for sample, it might be worth collecting a sample from an area adjacent to the item or the targeted area, an adjacent area, to the targeted area where possible, or to collect items from the crime scene that are similar to the item of interest. So if the item was, say, the exhibit was a knife, potentially collecting other knives. Items in immediate vicinity of the item of interest, so say in a situation where a gun was found under a pillow, might be worth also taking the pillow or collecting the pillow, as well as collecting reference profiles from known regular users and associates of the persons of interest or wearers of clothing. So moving on to DNA recovery. This relates to the process of targeting, sampling, extracting, and analysing a trace. In the interest of time, I won't discuss recovery in detail, but I just wanted to flag a few key points. Initial collection is crucial. It impacts the rest of the process. So we need optimal methods for each sample type to ensure that DNA collection is maximised. And there are a variety of collection methods available for different sources and different substrates. And studies have shown us that there are differences in the collection and extraction efficiencies for different sources and substrates. And so it rests on the laboratory to determine the best sample recovery method given different sample types and the suite of methodologies that are in use by the laboratory. Targeting is key when collecting samples, so both sampling beyond the target boundaries and only a portion of the deposit have downstream implications. Knowing where to target when dealing with contact traces is really important. Unfortunately, we have limited techniques available and information for this. Examiners are really left to rely heavily on case-specific information and visual analysis of the exhibits. However, lab success rates are not only important for understanding lab performance, but they can also be used to assist in sample targeting, among other things. In addition to collection methods, the suite of methods used by a laboratory, from extraction through to profiling and interpretation, have been shown to have an impact on the quantity of DNA retrieved as well as profiling outcomes. And this has been shown to result in different probabilities of DNA TPPR between laboratories. So what I just wanted to show here is that care must be taken when using published data for activity level assessments. In summary, different labs use different methods from collection through to interpretation, and these are going to impact the amount of DNA retrieved, as well as the reportability and the composition of profiles obtained, and they can potentially result in different probabilities of DNA TPPR. So as I said earlier, it's important to consider the source of the data used to inform activity level assessments. So now that I've just completely overwhelmed you all with all the knowledge that we have on DNA TPPR, you're probably sitting back wondering, this is all great, but how does it apply to casework? And we need more data given specific situations. Well, there have been numerous publications demonstrating the use of DNA TPPR data, and they show the importance of considering activity level propositions when evaluating forensic results. This here is by all means not an exhaustive list. There are many others, and I didn't want to dwell on this because there is another presentation on activity level reporting, as well as the hierarchy of propositions. So I hope maybe you'll find these useful if you wanted to go back and have a look at the slides. And on the point about more research, I would have to agree. On more data, I would say, I would have to agree that yes, we need more research. There's been a lot of interesting work in this space, as you've seen. I've presented a lot of it today, but there is much more that's needed on the core variables that impact DNA TPPR, as well as mock simulations of casework scenarios. A greater accessibility and sharing of data will increase our awareness of DNA TPPR associated issues. And hopefully one day we'll have a centralized database of DNA TPPR data. That would be a dream. The availability of relevant casework information will also help those who are evaluating DNA results given activity level propositions, and also those who are performing research as well, to inform research directions, I suppose. And so that's it from me. Thank you so much for your time, and yeah, thanks for joining me.
All right, so that concludes our presentations for today. And I would like to thank you all for joining us. I'm going to share my screen again to show you actually a very recent update that occurred in the last talk in response to the question about database searches. Klaus Fluten offered to put together a presentation, which I've added to the schedule for our next webinar, which is going to be on July 17th. So I'm looking forward to that as well. So I would like to thank all of our speakers for joining us today and sharing their expertise, as well as thanking our hosts today, Tyler Rabel and Lauren Mangum in the background there, and their colleagues at RTI for helping us put on this webinar today, as well as the support of Jerry Laporte and others at NIJ. Thank you all for joining us. I look forward to seeing you come back on the 17th. And I will, with that, pass it back over to Tyler for final comments. Thanks so much and have a great day.
All right. Thank you so much, Dr. Moretti. We'd first like to thank our subject matter experts for taking the time out of their day to present the material for today's workshop. We'd also like to take this time to thank all of our attendees for joining us today. This probabilistic genotyping workshop series wouldn't be possible without your attendance and support. Before you leave today's event, we would again like to ask you to participate in a short survey. You'll find the link below the closed captions pod on the right-hand side or on the main workshop page. Your feedback about our events is vital information that we use to provide the best experience possible and adjust the content and the way we disseminate that content to our audience. So if you could take a few moments and complete the survey, we would greatly appreciate it. Just to reiterate, we've recorded today's module as well as all of the modules leading up to this, and we'll be turning them into archival versions over the next couple weeks. The first few archival versions are ready for registration and can be viewed whenever you so desire. And we will send out notifications to alert everybody when this module is ready to be viewed. So we're also going to be putting our social media outlet information as well as our podcast information in the chat pod. So go ahead and follow us on Facebook, Twitter, LinkedIn. I think we're also on SoundCloud, and you can check out our website. If you want to stay up to date on all the latest offerings that are coming out of the Forensic Technology Center of Excellence. Again, we'd like to thank everyone for attending today's workshop, and we hope that you found the entire event both useful and informative. Make sure you complete today's survey and also visit us at our website at www.forensiccoe.org to check out our complete course list. Thank you again for attending, and we hope everyone has a great day.